There you go, sir. Next year, I'll come in with the Texas drawl, and you'll get it all. Yeah, 100%. All right. Thanks for coming. Thanks for day 2. Hopefully, everybody had a great day yesterday. Not a long speech, I promise you. But thanks for coming. Most importantly, as Paul asked me to remind you all, if you didn't hand in papers, school papers yesterday, please hand them in today if you can. And then, of course, today, if you have papers, and if you don't have a paper, go get one from Paul at the back. And please mark them up. It's very important for the people that come up here and do their work to see the feedback from everybody in the audience. So please do that. We're going to jump straight in. No need to hang about. So sit down. Hopefully everybody's good. The first paper today, Challenges and Benefits of Standardizing Process GC Applications and Solutions, is by Mike Rucker from Siemens and Al Kanya. Mike's going to present. Let me get his bio. What we got here? Yeah, come on up, Mike. Thanks, bud. Michael Rucker is the global head of standards. Oh, no, that's your title. What is your title?
My title?
Yeah.
Yeah, global head of standards.
Oh, you are the global head of standards.
Yeah.
Absolutely. Good job. Joined Siemens in 2004 as a run-out technician in Bartlesville, Oklahoma. Since then, he has gained significant experience working on all types of analytical equipment, process, and laboratory with companies like ABB, PerkinElmer, UVU Analytics. He's originally from Bartlesville, Oklahoma, graduated with a Bachelor of Science degree in molecular biology from Rogers State University, and he moved to Houston with his wife and 3 daughters in 2016. Mike likes being outdoors with his wife and teaching his grandson how to enjoy the outdoors. Please welcome Mike to the stage.
Thank you. Think this one's working? Okay, perfect. Okay, so we'll hop right in. I think let me get familiar with my pointer here. Not that I can do anything. So yes, Mike Rucker, good morning, everybody. Hopefully everybody's awake. Hopefully everybody had some breakfast, and we can hop right into this. So standardization, and I put here why standardize, but this is really kind of how to standardize. And when I say goals, these were also our challenges. These are the challenges we had to overcome. And then once we overcome those goals, we get these benefits. So really the first one here, broad scope of components and ranges. We want to look at this application. We want to look at the components that we're going to measure. And we want to break that. We don't want to measure, we want to do multiple analyzers and multiple sample points. And we don't want to measure the entire breadth of those components. We want to break it down into chunks so that that standard application has its fit. And we can fit multiple different applications together to get a holistic measurement. Ranges are important here as well. We'll talk a little bit more about that. Next bullet point, challenge here, to simplify that application and to modularize that application. So when I say simplify, we are wanting to take our method settings and we're wanting to hold as many of those constant as we can so that we don't have to change them from analyzer to analyzer, from application, or from module to module. And so we want to use the simplest application or simplify the application method. So backflush to vent, backflush to detector, and we'll talk more about that. And then we want to modularize that. We want to put it on in a box so that it can be taken out of the analyzer. It can be tested externally of the analyzer so that we know that this application will work long before we need to put it into that analyzer. Next bullet point, consistent and robust. This is the one you're going to hear me talk about a lot. Consistency, consistency, consistency. Gave a training on GCs just on Monday, and I kind of harped on this over and over. Consistency in that analyzer is what gives you a chromatogram that looks the same each time and puts things in the same spot each time. So we want consistent materials, consistent settings, and we also want those to be robust. Robust as in they can handle their environment that they're in, but also that they can handle changes in concentrations in those components in those ranges. So we want very robust and consistent settings as well. We'll talk more about that. So once we overcome those challenges, we meet those goals, the benefits we're going to get from these standard applications is definitely going to lessen that training burden. So we've got a module now with very few settings that can just be put into an analyzer and get that analyzer back up and running. We've simplified it we know where it goes, we know what analyzers it works in. So you don't have to actually know all the ins and outs of gas chromatography to get a standard application to work. That's the idea here. Fewer spare parts, of course. If we've modularized that and that application fits in multiple analyzers, multiple sample points, we only have a few. I'm creaking up here. I don't know if you guys can hear that, but I can sure hear it. So we only have a few modules to cover to fix multiple analyzers. We'll talk more in detail on that as well. This is a big one. This comes from this consistency and robustness, known capability. So this is part of the testing external of the analyzer, plus the consistent materials and settings allows us to vet out the materials, to test the application thoroughly. So we know exactly what components it can measure and at what ranges. We know what issues it might see. And in that is a lot of power when we know that capability. That gives us kind of a gold standard or model chromatogram that says this is what your application should look like. And if it doesn't look like that, now we can start to leverage that knowledge to say, okay, what's going on in my analyzer? Really kind of the health of your analyzer from that gold standard. And this goes right into the next bullet point, known interferences. If we know the capability, we also know where any interferences in that stream composition might come out. Those might be interferences you're expecting, and so we'll compensate for that. Or those might be interferences that you're not. There might be some breakthrough that's happening. And so we now know with a standard application what that extra interference is, and then we can start to diagnose the system where it's coming from. Quick replacement. This modularized approach, this consistent method settings allows for basically just swap a module out, put a new one in, very few settings, and you're back up and running. These last three are basically the same. Minimal settings to be changed. If we've overcome that challenge of consistency and simplification, there should only be a few settings, not a whole bunch. And they should be settings that, since it's external, have already been basically verified, vetted. We know what settings we need to input. Should be right there on the module. And we'll look at that. All of this adds up to reduce downtime. For one, if we have a model chromatogram, if we know what that application can do, we can now kind of understand the health of that analyzer as it's running by looking at different factors. So we can predict possibly our downtime, so now we can almost schedule downtime. Or if we actually have a failure in that application, with the quickness of changing out a module and the ease of just a few settings, within 30 minutes to an hour, that analyzer's back up and running. And with that lessened burden of training, your resources, your pool of people that can actually fix that analyzer is much larger now as well. There we go. Okay, so now we'll start to go into some of those challenges and how we overcome this. So when we're talking about broad scope of components and ranges, like I said, we don't want to take the application. Let's take natural gas, for example. You've got, 12 components there. We don't want an application that necessarily covers all of those in one application. We want to break that up into pieces. And by doing that, that application now that we've broken into pieces can fit in multiple different analyzers. It doesn't have to necessarily just be natural gas. It can be, and I'll show this on the next slide, it can be different sample points. It's going to overlap. All those components will overlap. And you can see I've got a couple here. That's it, that light fraction, nitrogen through acetylene. That's one application. And the next application is your propane, your 4s, your 5s, C6 plus application. And so with both of those, kind of a plug and play, mix and match, we're able to get that whole holistic measurement. And I use natural gas because we all kind of know the components that are there quickly. But those components reside all over the place. So if we can mix and match these applications now, we can cover a large breadth of sample points, a large breadth of analyzers. So here we go. Here's the slide. So we're kind of looking at, this is just a quick, generic pick of a few towers here. and just basically generic ranges of those components. And so I'll talk about that. So the overlap, you can see the red, the 101 is what we call it, but that is an application that does the nitrogen through acetylene. Well, it's going to have overlap in a couple different sample points there, methane, ethane. And we also have another one that does our C6+, our propanes, 4s and 5s. That also has a couple different fits to fulfill that holistic measurement. What that does for us is lessens our spare parts, because now we just have that one module that can fix multiple analyzers. It brings down that training burden, because all that technician needs to know now is what modules can fix those analyzers and what settings I need for those modules. And so that in itself starts to really help our industry with the standardization. And I got to get to going a little faster here. Ranges. This is very, very important. So typically in our world, we always spec everything out 0 to 5%, 0 to 10, 0 to 100. I would challenge anybody in this room to measure 0, ever. I'd also challenge you on a 0 to 100% application to measure 1 ppm. So in a standard application, that's why we want to scope those components and those ranges. Is because we want to know that we can successfully measure from 1,000 parts to 100%, or maybe down to 200 ppm to 100%. And if we do have applications that we need to measure lower ppm level, that's a different application. We come up with a different set, because that consistency that we'll talk about later is very important. We can't be changing every single time. Simplified. This is important because of what we were just talking about, that consistency. We want to simplify the bits and pieces that are going into this application. So of course, we're going to talk about backflush here, and that's what we're utilizing most of the time. The components that go into that, we want consistent materials, consistent sample loops, consistent valve, consistent columns, and we need that to be as simple as possible, so that we don't have a whole bunch of method settings we need to think about whenever we swap out this application. So the simplified application allows us to hold some of those method settings constant. Retention times, backflush times, those don't change from module to module of the same application. With that consistent material, it's going to stay the same. So there's only a few settings, EPC pressures, to get your flows correct, line everything up. All right, so we'll get to the real meat and potatoes here, this consistent and robustness. So you can see the chromatogram. It looks much better here than it does on my screen, the big, huge screen, so you can see it. That is an overlay chromatogram of multiple different analyzers with the same application, right? Same module, same application. And you can see propane there. I think that's 35, 40 seconds. On each one of those analyzers, analyzing propane, it's at the exact same time, every single time. So if you want a propane analysis, propane is going to be at 40 seconds. When we do that in the way we're doing it here in a standard application, I now know any analyzer that I have with this application, propane should be at 40 seconds. And that in itself has a lot of power. I also know where my 4s are. I also know where my 5s are. I also know where any interferences might come out in between there. So I can start to have some of that predictive, preventative maintenance when I see things that are out of the norm. And again, that consistency all comes from consistent materials and consistent settings. That gives you that consistent chromatogram. Typically in our world, if you're measuring propane at this refinery and propane at a different plant, they've probably got different applications. With this, standardizing, it's the same every single time, so you know what to tell somebody if they're having a problem. Consistent material, so we'll get into that. So, like I said, simplified, it's on the module. We have basically put guardrails around what components and ranges we're going to measure so that we can make it a backflush, and with those ranges, we're going to say it's a certain size sample loop, 22 microliters, let's say. That's going to be consistent each and every time. It's the same. It's consistent material, the same lengths of tubing, the same restrictors, the same valve, the same columns. And even a step further, same packing material in those columns. And that needs to all be consistent and vetted out. So we've not only tested that and looked at that to make sure that that works how we want it to each and every time, we've also made the manufacturing consistent. So that each one of those modules lends itself to the same chromatogram every single time, no matter what analyzer it's in and what sample point. And so this last bullet point here, with that standard application, standard hardware, we can now test it. We can now bounds test is what I call it. I don't know if that's the right name for it, but we can bounds test that application, and basically that's where our model comes from. This is kind of what that looks like. It's a little busy up there. It's meant to be. So bounds testing is that qualification of that standard application. So I know it's going to look the same each and every time. So I can run multiple different stream compositions at different levels. I can run those interferences. I'm stress testing it. What can this application handle? What can it not handle? What is going to cause it to fail with interferences at what levels? And I do that on enough instances to statistically say, going forward, this is what that chromatogram should look like. And now I can start to leverage that in predictive and preventative maintenance to say, okay, when that moves around a little bit, okay, that's normal. But if it moves past this point, I've got something going on. And so I need to come either get a module and get ready to swap that out or try to figure out what's going on with my system. That all comes from this testing, this vetting of those applications. A lot of time goes into that, but it's very well worth it. So again, consistent and robust. So with that testing, with that characterization of the application, I now can come up with settings. So propane. We all know that propane is 1,000 ppm at 40 seconds. But at 99.9%, it's probably going to move. You're going to get matrix shifting on that chromatogram. But if we've tested it and we've characterized it, we statistically know that it's only going to move so much. So I can set up a window to make sure it's always underneath that window. So no matter what composition, no matter what range within what I've spec'd out, it will always measure that. And we know that. That's with those method settings held constant as well. So that retention time, we never need to change that retention time. It's always the same. The backflush time, we've created this application, right, with the right columns, the right materials, so that backflush time never has to change. So I'm always getting the components of interest and backflushing my heavies each and every time. The only thing I need to change are my EPC pressures, which are indicative, or which basically give you the flows you need to line everything up. Once that's there, everything else works. And this is just an example of that. So that's robustness in settings. You also want to pick materials that are robust, that can kind of handle the environment that they might be in. It's a module, so it's going to be in the ambient atmosphere, when it's coming to and fro to the analyzer. So your mole sieves, that would be the example I would use here. If you had mole sieves in there, it's probably going to have issues when you take it out and get air and moisture in it. So we want to pick materials that are robust enough to handle being handled and to handle atmosphere, things like that. So that's part of that actual robust materials. That allowance for variance in composition. So these two pictures here, the top chromatograms are two different applications, so two different modules, tested at different times, tested on the same blend. So they look a lot similar. But then the bottom is when those two modules were basically come together for a holistic measurement for somebody. So now we've taken two different building blocks, brought them together to give you the measurement you need, and it shows basically the change in ranges of those compositions and how through all the testing we're able to compensate for any variances there. Those modules were tested, sat on the shelf for a month or so before they were actually brought together for this analyzer, and this shows that robustness is there. Gives us confidence. Last but not least, that reduction in downtime. So we've covered a lot. So we know the components we want to measure. We know the ranges. We've basically made it as simple as possible, so there's very minimal settings there. We've put it on a module, in a module, however that looks. so that it can be all of that hardware, valve, columns, sample loop, everything that's a part of the application can be taken out in one fell swoop. And so with that, you have a failure, we can take that out, put a new one in. All we need to wait for is for that oven to heat up. Different oven types can take, that might take a different amount of time. Calibrate, or put your settings in and then calibrate, and that analyzer's back up and running. So anywhere from, for hours, it's around 20 minutes of downtime. Different oven types, it may be 30 minutes, maybe an hour. That's still much, much less than if you were to change out a column and you had to actually adjust all of those method settings that we're trying to hold constant. It's also can be done by a technician that can just turn a wrench. So this room is full of experts in chromatography and things like that that can help, okay, we need to adjust this or that. But we have a lot of people out there that need that, okay, I just need to put a module in and get this thing back up and running. That's it. Put in your EPC pressures, everything lines up, calibrate, and you're back up and running. And that's it for me. Any questions? I either did a real, okay, I got one down here, okay.
What type of temperature does this go up to?
It can, so basically it's just chromatography. So we can standardize on any temperature. But that's a very good point. That temperature needs to stay consistent as well. So whatever we apply that application to, 60 degrees C, 80 degrees C, 100 degrees C, that oven temperature needs to stay the same as well. Otherwise, your method settings are going to change. Yep.
So what would be the cost impact? Because now you're pulling modules and throwing it into the oven versus just developing a specific application. Is it cheaper to make, or now it's going to be more expensive because you have separate modules that you have to bring in and to set up an application?
So if you look at that holistically, cost-wise, it's cheaper in the long run for sure. Sure, you're swapping out that module, and that's a lot of hardware, but you're doing that very quickly with not a lot of know-how. So so it's definitely a cheaper way of doing things. Makes things easier for everybody.
It does bring on the vendor, the manufacturer, work on the background to make sure you can support that in the field, because that's always a challenge to have lead times on quote, lead times on repairs. So it would definitely, I mean, it's a great idea, but I think on your side it has to be well supported. So if we're pulling a module and now we're saying we don't have the more experienced people to handle it, some customers might be expecting quick turnaround.
So that's
or have a spare on the warehouse, and that's some money on this side.
But that's the beauty of a standard module, right? Is yes, it's basically a spare part now. It's its own spare part. It's the combination of all those parts, and so that's with that robustness, that shelf life. The idea is if you don't have it on the shelf in your warehouse, we have it on the shelf in our warehouse. So it's not a matter of, okay, I've got to figure out what application that is. We have, you've got a set number, and those are ready to go. And that's the other point of scoping your components. If it was that entire application, that's very specific for that one sample point. But when we make it into smaller building blocks, this can fix multiple analyzers. So that one part can get multiple analyzers up and running.
Hey, Michael. So I had a question for you on Monday, and it was considered, talking about the columns, right?
Yep.
And I was asking about the shelf life.
Yep.
So here on the module, now we're specifically talking about Siemens. So for Carbo Black or mostly like you're talking about, can you share what the shelf life is if I was to change out a module, not knowing if that column is a month or a year old? How can I identify that before I swap out the module?
So our modules are all serialized, and so they all have a date. There's a date somewhere on there, and that's it. We talked about this on Monday. Each packing material, everything has some sort of shelf life. Some of that's very long. Much longer than that analyzer, then we're going to end up swapping it out at some point. Some are less, and that's just a matter of knowing that as you get those certain types of modules. Now, what we've done, and that's what I shared with you on Monday, always try to pick the most robust material that has that longer shelf life because of that. We don't want things not working within a month. We want them to last months, years, if possible. All right.
Hello. Our next paper, our second paper of the day, is by James Tomlinson from Elemental Enterprises. He's the product manager for Elemental, a biophysicist, and has worked in analyzers and the process analyzer technology since 2000. And I'm guessing your hobbies are nanogravimetric detectors for gas chromatography. Is that right, James?
That is correct.
Please welcome Jim to the stage.
And old cars.
And old cars.
So I've worked with Mike peripherally a couple of times just in the industry, as we all have worked with other people in this room. And we were yucking it up, being buddy-buddy before the talk, and then he stole about half my material. So not sure would be his buddy-buddy next time, but that's okay. So we're going to be talking specifically about a new technology for micro GCs. You're going to hear a lot of the same things that he was talking about in terms of modularized and swappability, that sort of thing. But we have a particular detector that we're using now, and that's the NIMS or NGD. We've got a couple of slides here we'll skip over pretty quick. That's the who we are. Elemental is we're a rep and integrator with a bunch of experience in the industry up in Montgomery, Texas. And Apex is the developer of the detector, the NIMS detector. They worked with, was it Caltech? Yeah, Caltech, and another university in France on developing this, as well as working with the actual manufacturers. So what are we talking about? We're talking about an additional detector technology for gas chromatography. NIMS and NGD, you'll hear us use the terms fairly interchangeably. That's because they almost are the same thing. NIMS stands for Nano Electrical Mechanical System. We'll get into why here in a minute. And then when you call it an NGD, you're saying nano gravimetric device. One is a more specific kind of the other, but it's pretty much the same thing. So what it is an electrically driven resonator with an active site coated, and in fact, because it's a chip, it's all coated, with an absorption-desorption media that you see on a column that attracts the hydrocarbons. We drive the resonator with one coil. Essentially, this is simplified. We drive the resonator with one coil, measure it with another, and when something sticks to the active vibrating beam, it slows down. And then we measure that frequency change and the time that this stuff takes, and that allows us to calculate what has been stuck to the resonator. So we've got some pictures here. So in our case, the white board, that is the detector element board that we're using. You see two stubs of column material that are coming out of it. One side would be the reference, and one side would be the measurement channel. And they're printed on a big wafer in the foundry. And to go to Mike's point that he kept talking about traceability of materials, we're making all these things at once. And if you know much about the foundry process and the making of these big wafers, they're all pretty much the same. They do have to be inspected to make sure that there's consistency across the element, but they're all made at the same time in the same place. They might as well be the same thing. And then we use arrays of them. Oh, I see. All right, here we go. Getting used to this layout display. I wasn't sure what you were seeing, but now I get it. So we have a resonating structure with the chemically attractive layer. And when something sticks to it, and the next slide shows us a little bit better, it causes the resonance frequency shift. It slows down. So here is what we're talking about. You can see in the box up at the top that says NGD. This is a comparison, a couple of chromatograms on the bottom. But it's showing that when the analyte passes by the waving rod, it sticks to it because it's attracted to it just like it would be attracted to any affinity column, and you experience the absorption-desorption process, and while it's stuck there, the resonator moves slowly, more slow, and we can measure that. And then we use a bunch of devices, 25 connected in parallel in an array. The noise between one device is uncorrelated to the others, and the limit of detection is improved because you're doing basically lots of sampling, lots of math. So that shows, you can see in the right-hand slide, you see the driving. You want me to explain this? Okay. But that's the resonator. You can see the resonator in the middle that moves back and forth towards you and away from you. So why NIMS? It's an additional sensing technology. Who doesn't want something else to use to look at things, another tool in the toolbox? It's sensitive and best used for the heavier compounds. So C6 plus, we can go, in gas mixtures, you're talking 12 and 15, 16, but we can also do liquids with this detector. You don't have to have fuel or makeup gas. It is non-destructive, so it can be used in line with other detectors. We're doing that now. We'll talk about that in a second. It does have some carrier gas sensitivity. What doesn't? But you can use air as the carrier gas. And it is not sensitive to light hydrocarbons. It's one of the drawbacks to it. But we put the detector all in one module. So this is the micro GC module. You see it on the left. And we've got the valving, the column, the detector, all in the heater, all in one module. And the modules can run more than one method depending, but it's a modular method is linked to the module system. So we have different modules that we use for different things. We can temperature ramp if that's necessary. We do the heavy modules for C7 to 12, and for gas rather, and then we can actually do the liquid injection module as well. We've got lab packaging. We've got the Chromex 200 and 400 are ATC certified environment instruments, and we can put the combination of sensors anywhere you need to. So this is showing alkenes, C6 to C13, and you can see the limit of detection linearity there versus the number of carbon atoms. And we've got a couple of application slides, C6 to C13. And you can make any of the calorific value calculations, hydrocarbon dew point, and then trace gases in stuff like biomethane. And then here's a detector for NGD for environmental applications. And we also have the liquid measuring module. And we can look at other fluids as well. Now, wait a minute, let me back up. I'm missing a slide. No, I guess not, just in my head. So we can measure the lights with the TCD, standard technology, but we can also put the NIMS detector in the same module and run them in line because it's non-destructive. We can put the NIMS in front and then use a standard detector all in one module and get all of your measurements in one small package. It is modular. That's why I was complaining about Mike stealing my stuff. But the modules do go directly into the units, and the method is paired with the module. And when it's not working right, you don't trim columns, you don't do that sort of thing, you just simply replace the module. And I think that's what we've got. So we've got, it's all in one. We can measure most of the things you're looking for. There's instruments in the field doing this right now, all day, every day. It's less expensive for the same reasons Mike was talking about modularity. It is small, and you can train your people quick, and you can do lots of different things with them. Because it is a modular setup, you don't have to have a guru doing all the work on it. So that's what we got. I'm the quick one. Any questions?
Anybody have any questions for James? One? Al? Can you grab the mic behind you? Thanks, Al.
Yeah, you talked about how the compounds will stick to the oscillating doohickey thing.
Mm-hmm.
How does it unstick?
Absorption, desorption. It's just like it acts in a column. I mean, it's the whole tennis ball and the Velcro analogy.
Any more questions?
Oh,
What's the typical analysis time?
typical analysis time through the module is about 2 minutes.
Your coating that you put on there, does that wear out? What's the life?
Right, it's a porous oxide. I mean, a high temperature, I don't know the answer to your question, but physically wear out, I don't know.
Which components the NGD cannot measure?
The lighter, it has to be large enough to slow down. So C6 and plus is what the NIMS is measuring, because below C6, there's not enough mass to slow the resonator down enough to measure. So that's
That's for the hydrocarbons, but how about the other components? Doesn't matter as long as the mass is.
correct.
Thank you.
I didn't,
Oxygenates and alcohols.
oh, come by the booth. Ask that question. That, now you're in the weeds, come by the booth. No.
Okay, that concludes the first session of the morning. There are refreshments and a break in the vendors hall, and back here for 10:15, please. Sharp. Thank you.
Ready to start here, the second session of the morning here. It'll be focusing primarily on emission monitoring solutions that we'll have papers on. And we have 3 papers, so we'll go ahead and start promptly. I don't want to drag things on too long so you're late for lunch or anything like that. Again, my name's Al Kanya, and I'll be your moderator. Our first speaker is John Callum. He's from SICK, and he'll be talking about the importance of accurately measuring NOx emissions accurately. He's a native Texan, woohoo, BS degree from Texas A&M, and an executive MBA from the University of Houston. His hobbies are reading, do-it-yourself projects, hunting, fishing, and golf. Let's all welcome John.
Thank you. Good morning. Can you hear me in the back? Having a degree from A&M and from U of H means I bleed both red and maroon. So we'll go ahead and get started here. I thought we'd do a little bit of a primer. I know this crowd knows what NOx is, but it's oxides of nitrogen. It's very reactive. It's usually created from a combustion process. I'm not going to read this whole thing here, but you can if you'd like. But I thought what was really impressive when I was doing the research for this is the great strides that we've made over the years. Since the Clean Air Act in the early 90s. Most of us in the room here remember that. And, we've done a really good job of reducing NOx emissions. 70% since 1990, we've reduced the amount of NOx produced in the U.S. So where does NOx typically come from? When I was doing the research, I kind of realized that, automobiles are a big component of that, and they're about half of it, 50% of the NOx from the transportation sector. So that's from cars and diesel-powered, big rigs and things of that nature. But the other 40% is something that we can affect, and it's from a combination of industrial, residential, electrical power generation, combustion applications. So I'm not sure how well that's coming out, and you can read it. But the basics of this is every fuel has its own NO potential, based on one, how much nitrogen is in the fuel, whether it be coal, whether it be gas, whether it be waste or oil. All of them have their own resonant NO potential, producing potential. Some of them, if you burn at a higher temperature, you produce more NOx. So NOx, as we said, was a product of combustion. If you have incomplete combustion, you're going to have higher NOx. If you have too much excess air coming in to your combustion process, you're going to be bringing in outdoor or excess air, and that's mainly 80% nitrogen, so you're introducing more NOx that's going to go up the stack. Obviously higher nitrogen content fuels are going to produce higher NOx levels as well. So is that an ugly picture or what? I tried to find the most ugly photo I could out there. This is not Houston, this is LA, but if you're making your commute in Houston early in the morning or late in the evening or late in the afternoon, the sun's starting to set, if you see that brownish colored haze out there, that's the NOx component. That's the NOx in the air. So why would we want to measure NOx? Obviously, to meet the EPA standards, make sure that we don't get fines logged against us as producers of NOx. Also, NOx, when it gets together with its sister, VOCs, volatile organic compounds, it produces smog, ground level smog and acid and rain. And these are things that are very detrimental to humans and animals when they're taken into your lungs. It causes sickness and also can lead to death as well. So how do we remove NOx? There are several methods of denitrification or denox to reduce NOx emissions or eliminate them. One we talked about earlier was just optimizing your combustion fully. You can reduce the NOx levels. Implementing a low NOx burner strategy, or taking your exhaust and run them to, say, a waste heat boiler. So there's a lot of different strategies, but the two that we were going to focus on today is the scrubber, two types of scrubbers, the SCR and the SNCR, which is the selective non-catalytic reduction and selective catalytic reduction. So when I'm talking to people who are non-technical, I'll say this is similar to the catalytic converter on your car. And I hope everybody's catalytic converter is still on your car when you leave this exposition, because there's been a rash of thefts. And so why would people want to steal your perfectly good operating catalytic converter that's on your car that's removing the NOx from your emissions? Well, there's metals in there like platinum, palladium, and rhodium, which can be recycled and can be sold. They have monetary value. The SCR has a catalyst on a bigger scale, and the SNCR doesn't have a catalyst, so you directly inject ammonia, and then you convert the NOx to nitrogen and to water. The SCR has the catalyst. You use ammonia injection prior to the catalyst bed, and then have that same conversion of NOx to benign nitrogen and water. Looking at the two strategies, the SCR uses less energy and is a more efficient means of removal, but the catalyst cost, you have to factor that into your decision making. The catalyst is a little more expensive as well. How can you enhance your SCR control and make sure that you're removing all the NOx, but you're optimizing its performance? One of the ways that you can do that is to have a in situ NOx measurement prior to the scrubber, giving a feed-forward signal back to the ammonia injection control loop to minimize the amount of ammonia that's going in. It's kind of like the Goldilocks thing. You don't want to have too much, don't want to have too little. Also, you can have another in situ analyzer or extractive analyzer measurement on the downstream side of the converter or the scrubber itself, measuring both NOx and ammonia, so that you can finally dial in the ammonia so that you're not getting too much. Because if you get too much injection, you're going to reduce the life of your catalyst. And not enough, then you're not going to have a full reaction. You're not going to remove all the NOx. If you have over-injection, you end up corroding the equipment downstream, and so you have failures due to corrosion and lots of cost, MRO cost or maintenance cost. If you extend the life of the catalyst, it's very expensive, a lot more expensive than your catalytic converter replacing it in your car, but to replace that is very expensive. So there's cost savings for dialing in and optimizing your ammonia injection. Also, ammonia is not cheap. It costs money. So if you can reduce the usage, you reduce your operating costs as well. So the advantages of doing it in situ is you have a lower total cost of ownership, have a real good representative, very fast measurement for your control loop, and you can fully optimize the scrubber. And if you have gases that could possibly condense, there's no chance of doing that when you're actually doing the measurement in situ, because you're not modifying the sample at all. Two other topologies and two other strategies that can be utilized as well is cold dry extractive and hot wet extractive. Both of these would require a sample system, and we all know in this room the best analyzer cannot operate properly unless you have a properly designed sample system. The cold dry sample system requires a little more complexity, more consumables, and has a higher operating cost on average. The hot wet extractive analyzer, we keep it above the dew point, keep it hot from the sample all the way through the analyzer. It's good for applications with high particulates. It's good for making measurements where you have condensables like HCl or HF, some acids that would condense out if you tried to chill them. So the conclusions that we come to is we really need to measure NOx. We've done a good job of reducing NOx, but there's significant means to decrease NOx in industrial applications and provide better breathing air for each and every one of us and our children that come after us. And then if you apply the ammonia slip NOx in situ analyzers, you can optimize the performance, you can reduce cost, and you can save money on capital equipment. Also, the in situ measurements are very fast responding, they're very representative, and they will decrease the overall need for maintenance. Also, would mention that cold dry and hot wet extractive, if they're properly designed, can do these measurements as well, but you will have some inherent delays due to the sample lag times. So there's many factors that are going to play a role in what decision you make and what analyzer that you use. Some of those are based upon what you're burning, what type of fuel you're burning, what are the regulatory requirements, how much space do you have up on the, how much access do you have to the sample points. So there's a lot of things that go into making that decision. But I welcome you to come by our booth, talk to our experts, and we can tell you the relative merits of each one of these type of topologies to make this measurement. And we look forward to seeing you over at our booth. Thank you.
Do we have any questions? Oh, geez, sorry about that. Do we have any questions before we leave? Alrighty then. Well, like I say, you'll be able to catch them a little bit later in the booth and such as that. So thank you very much, John. Oh, thank you. Yeah, thank you. Thank you. One last round. One sec while I get ready for our next presenter. And close. And, oh, he's over there. Oh, there we go. Love it when it works. All right, bear with me. Yeah, our next speaker, as he's getting ready here, is Jeremy Stein. He's with M&C Tech Group North America, where he's a project manager and field engineer. He's a project manager and field engineer for M&C Group North America. He has a decade of experience in the continuous emission monitoring and process measurement systems fields, including multi-point averaging array. He has designed both compliance and process monitoring systems for a wide range of applications, including various refinery, chemical plant, coal-fired wet and dry FGD systems, gas turbines, biomass boilers, cement, steel, and renewable wastewater and landfill gas applications. His hobbies are adventures with his kids and camping. Come on board, Mr. Jeremy. Give me a hand.
Should be. Okay.
Hey, you're on. I can hear you.
Okay, let's see. Okay. All right. Everyone, good volume? Okay. Hello, everyone. As noted, I'll be speaking about measuring low-level sulfur dioxide concentrations in the presence of high ammonia levels in the process stream. Before I start, I'd like to thank a few people that were involved with this project for designing and manufacturing the sample conditioning system, as well as testing and modifying the equipment in the field. First, I'd like to thank Cliff Gordon and Tim Kiken for the opportunity to work on this project. I'd also like to thank the folks at Marathon, both Ryan Mead and Lee Robeson, as well as all of his technicians. They were instrumental in bringing this project together, really working through the problems, and made a huge difference in the design. Also, John Tryon from Mangan Incorporated played a very pivotal role in solving the issue, or helping organize everyone to work together on the project, and doing a lot of the legwork in terms of documenting things. And so without the team together, none of this would be possible. So a brief overview of what I'll be speaking about. First, it'll be a little background of the project, why we were there, and what our proposed system designs were to address the issue at hand. So I'll cover some of the thoughts and concepts behind our design, and then finally why we chose the design that we did. Once I cover those, I'll detail the components of the design and why we chose each component. And then we'll get into the real nitty-gritty with how we optimize the system, what kind of faults and fixes we came across during testing, installation, and eventual audit. And then also the final conclusion will be what we learned from the project and what our goals would be going forward with further improvement of the design. So a brief overview. The background for this project was measuring low-level sulfur dioxide for a compliance system. What made this particularly difficult was the elevated levels of ammonia due to an aging SCR catalyst. The refinery that we were working with was in an air district, or South Coast air district in Los Angeles, that they were looking to add sulfur dioxide measurement into their compliance regimen. And this was something that would require some modifications to their existing systems. The existing systems were already measuring NOx, CO, CO2, and oxygen. So a big portion of this project involved keeping that existing system in play to stay in compliance while being able to modify the system to be useful for measuring SO2. This would be a little bit of a challenge because the high ammonia levels and SO2, as you know, with moisture, cause a significant challenge with reacting the ammonia and the SO2 and condensing it in the sample stream, which can lead to sample loss and loss of accuracy, especially with low levels of SO2. For this process application, we were looking at SO2 levels of definitely less than 10 ppm, and for the most part, less than 5 ppm concentrations. So in order to address this issue, we considered multiple concepts that M&C has used over the past for applications such as this, or at least similar to this. Some of these approaches involved using phosphoric ceramic burl saddles, basically a phosphoric scrubbing media up at the sample probe location that would be useful for reacting with the ammonia and scrubbing that at elevated temperatures. The one issue with this is it has its limit with ammonia concentrations. It is a consumable, so with the higher levels of ammonia, our concern would be that they would be chewing through the scrubbing media very quickly. They didn't want to be replacing the media every week, so that idea didn't really seem feasible. So the next idea was to keep the system heated above the condensing dew points, and the reaction temperature between ammonia and SO2. Ammonia and SO2 like to react at temperatures below 200 Celsius or approximately 400 degrees Fahrenheit. So with that in mind, that would require a very hot sample line that would run hundreds of feet, and that would be very costly and difficult to implement. They wanted to refrain from doing that and keep as much of their current system in place as possible, both for compliance reasons and then also the feasibility of their budget and design considerations. So that was not an issue. So the final option that we came across was, let's see, so with these restrictions in mind, the final concept drawing concept that we decided upon was sort of a hybrid method of keeping the system hot above the reaction point of 400 degrees Fahrenheit up until we could find a way to scrub the ammonia and then use a system of scrubbing that didn't require a consumable, so to speak, that would be needed to be replaced every week. The scrubbing saddles or the saddle media is something that would be in a vessel. You'd have to empty it, rinse it, refill it with media again, install it, and that was something that was a little more labor intensive than the customer would have liked. So we formulated the idea of using phosphoric acid still, but in a dosing form, so basically a fluid injection. The fluid injection that we would use relied on the concept of basically reaction or equilibrium coefficients. Basically, phosphoric acid and ammonia have a quicker reaction constant than ammonia and SO2. So in plain terms, ammonia is a lot more attracted to phosphate than with SO2. So the idea was to use the phosphoric acid as a decoy to scrub the ammonia before it reacted with the SO2, and then condense that as the resulting ammonium phosphate salts at our scrubbing vessel, and that would allow the SO2 and all the other analytes to travel down a normally heated sample line to be analyzed. As you can see with the reaction, the phosphoric acid is a triprotic acid. Technically, it can feasibly, or ideally, it can react with 3 ammonia molecules, which makes it ideal compared to other acids, such as maybe a sulfuric acid or a hydrochloric acid. Also, it's a lot safer in terms of handling and a lot more commercially available. So it makes it a prime candidate for this application. One drawback with phosphoric acid dosing is, I said ideally it's a 3-to-1 ratio, but the phosphoric acid dosing, or phosphoric acid, anytime you get diprotic acids and triprotic acids, the dissociation constants drop by orders of magnitude. So dissociation constant of phosphoric acid when it still has 3 hydrogens is 10 to the negative 5, and then the second deprotonation is 10 to the negative 8, and then 10 to the negative 13. So it gets slower pretty rapidly. So when I performed the calculations for how much phosphoric acid we would actually need to scrub all of the ammonia, I assumed more realistically a 2-to-1 ratio. So 2 phosphoric acid molecules per, or 1 phosphoric acid molecule for every 2 ammonia molecules. The calculation featured the expected sample flow rate, the expected worst case scenario ammonia concentration, which was a fairly elevated ammonia concentration, and then based on the what was OSHA safe and what the customer would feel most safe ideally using, we decided upon a 10% by weight phosphoric acid solution for dosing. With the dosing, one of the other things that comes into play is how much would have to be used per day. So we wanted to make sure that when we were addressing the serviceability of the system, we gave the customer a realistic timeline of how long the acid dosing solution would last. So that came into play when we're speccing out systems. Before we get way down the road, we want to have the best idea possible of what kind of solution is the right solution. So as you can see, we tried to calculate out as precisely as possible to how many days a 1 liter volume of acid solution would last. So theoretically, we saw that it would last a little over 30 to 60 days. In practice, though, we, as you will see later, there's always the textbook answer and then the reality answer. So once we decided upon a acid dosing solution concept, we began getting into the actual details of the probe. One of the problems with the sample location, normally we'd like to keep everything compact and in one area. It makes the system design simple. And whenever you're transporting any analytes, there's always chances for loss. But on this stack, both the stack platform was very, very small. I would say there's probably 2 feet of space between the outside diameter of the stack to the guardrails. Also, the stack port was very low to the stack platform. So as you can see, it couldn't have been more than 1.5 feet above the platform. So if we were trying to incorporate a scrubbing vessel into our system, that would be next to impossible given where the sample location, the sample extraction point is, and where we would have to put the dosing vessel and scrubber. So what we did was we chose a location about 15 feet below the stack port. They had another platform that had a lot more room. So the idea was keep the system heated above the 400-degree Fahrenheit reaction temperature from the extraction point above. The extraction point, we used a coated, silicon arc coated SB 2020 sample probe, followed by a sample line heated to 400 degrees Fahrenheit with a silicon arc coated stainless steel tube, and moved the sample down 15 feet to a platform where we could actually have our scrubbing vessel enclosure. So the, let's see, I covered some of these already. So as you can see, SP 2020 sample probe with coated, wetted sample paths. It also used a coated stainless steel filter. And then the acid injection enclosure featured the the scrubbing vessel, as you would see, as you'll see in the next slide, as well as a heated Nafion dryer and our acid vessel and dosing pump. So here we have the general layout of the system. It featured our acid solution vessel, the dosing pump. The scrubbing vessel is item number 1. So that's where we would have our reaction with the phosphoric acid and the ammonia. And then followed by that, item number 2 is our heated Nafion dryer. So just to follow the sample path here, it's ammonia, SO2, and phosphoric acid would all be heated to 400 degrees Fahrenheit until they reach the scrubbing vessel, or the heated scrubbing vessel. At that point, the ammonia would react. We would drop the temperature down to allow the ammonia and the phosphoric acid to react inside the scrubbing vessel. At that point, they would form salts, and then the moisture of the acid solution and some of the moisture from the sample gas would condense and be rinsed down through our peristaltic drain pump. Any leaving the SO2 and some residual moisture and other analytes to pass through our scrubbing vessel into the Nafion dryer. And then at that point, the excess moisture that hadn't been rinsed through the scrubbing vessel would be dried from the sample stream in the heated Nafion dryer at point 2. So what really made this challenging was you have chemistry experiment upon physical chemistry experiment with temperatures and concentrations and reaction coefficients, and this all had to happen inside one box. So the probe and the heated sample line were above the 400 degree Fahrenheit limit. Then we had to drop that down to the scrubbing vessel temperature, which was we had at 140 degrees Fahrenheit. That allows it's cold enough to allow the reaction of ammonia and phosphoric acid to occur and the salts to form, but warm enough so that we're not scrubbing SO2 with the moisture. And then immediately after that, we have to heat the sample up back to the 230 degree Fahrenheit set point to ensure that SO2 doesn't react with the moisture once it leaves the reaction vessel. The other thing that came into play was phosphoric acid ammonium biphosphate salts are more soluble at elevated temperatures. So that goes back to the rinsing principle. Once those ammonium phosphate salts form, once the elevated temperatures of moisture, it'll be more and more soluble. So we have to get the reaction to occur, the salts to form, and then we have to rinse it so that the vessel doesn't slowly get filled up over time with salts and eventually plug the sample path. So many factors at play. So once we had all this designed, we installed it, and the system underwent system certification. Again, going back to the very low SO2 levels, we had to perform additional certification testing. Once the system passed 7-day drift tests and relative accuracy tests, South Coast required even more stringent tests due to the low sulfur dioxide levels, and the system passed those as well. I think the highest drifts that we saw were no more than 2% of span, so we can provide more details on that, but here we go. So as you can see, despite the low SO2 values and the high ammonia concentrations, we were able to actually get fairly decent repeatable results, both with daily span and during the 7-day drift and audit. So once we passed the auditing, we always have to keep the customer in mind. They have to meet compliance. But they were generous enough to let us continue to optimize this system, being that we, this is always everything we do, even though we've done it for a long time. Every application's a little bit different, and things can always be improved. So once we passed audit, we began system optimization to address certain pitfalls that we were seeing with the design. So specifically the acid injection rate, trying to optimize that so that the amount of phosphoric acid solution being used it wasn't higher than what was necessary. Also temperature control, the system when you're trying to drop out ammonia in one instance but then immediately remove moisture at another gets complicated. So temperature control within one enclosure became a interesting problem to solve. And then also just the amount of using different components that may not have otherwise been designed for our sort of applications. Think liquid chromatographs in a lab had to be retrofitted to be more industrious and rugged and fit, things like pipe fittings that we take for granted. So one of the things we did for this project in particular, we chose to use a variable dosing speed pump so that we could experiment with different dosing rates to see what was more effective and how we could address different competing interests. So based on the molarity calculations and reaction coefficients that we calculated beforehand, we were able to come up with what our flow rates could ideally be, sort of the range that we were looking for. If we had a higher, we could play around with more rinsing or more reactions to get better scrubbing of ammonia. Here's a lot of details that we can always do later. And then, let's see, acid. So one of the things I wanted to point out with this is you can see the tank duration that we expected for these values. If you had more flow than we could easily burn through a liter of phosphoric acid within weeks, and sometimes no one wants to do that. Let's see, acid injection rate with the dosing pump. One of the challenges that we came across was using a variable dosing speed pump. This was something that was designed for a laboratory environment where it wasn't, your ambient temperatures and pressures and, probably siphoning off a solution out of a beaker. But now we have to do this out of a closed vessel that's vacuum sealed so that we're not diluting our sample with ambient air. So there was a lot of fittings and tubing changes that we had to alter and experiment with so that we made sure we weren't either blocking the acid dosing flow or burning through too much acid through leak breakthrough. Another issue that we found was the temperature control of the scrubbing vessel itself. So controlling the temperature, having different heated zones and different cool zones inside the enclosure was a challenge. We had a 400 degree Fahrenheit. We're trying to keep sample at 400 degrees Fahrenheit and then instantly drop it down to 140 degrees Fahrenheit to get that precipitation to occur. That's a little bit of a challenge. So we found that the sample line was heating our vessel a little bit above the temperature that we would like, and we were seeing losses in SO2. So we wanted to, so what we did to prevent that was we used purge air that was specifically directed at the vessel that had multiple orifice holes to spread the cooling flow across the vessel so that all points were an even temperature. That was one way to keep the vessel cool so that we had more control with our PID controller. The other thing too was this purge air was used to keep the dosing pump within operation temperature ranges. But with the directed flow, we didn't create any cooling points where the acid could get, or where the SO2 and the ammonia could condense where we didn't want it to. So there's a expanded picture of that purge flow. So these were modifications that we had to make in the field. One of the other things that we came across, and it really shows that the reaction can happen that quickly, our original acid injection point was slightly above the inlet point of the vessel. As the phosphoric acid was dripping down into the vessel, it would meet the incoming sample, and it was actually reacting before it reached the vessel and plugging up the inlet fitting. So one of the things that we had to do was extend the actual injection point down into the vessel to prevent this from happening. It wasn't ideal because ideally we'd want a spread of that phosphoric acid so that it's more evenly distributed in the vessel. We were hoping that that elevation between the injection point and the vessel would cause it to spread more, but then we were running into this issue of plugging on the vessel inlet. So we extended it down into the vessel. This prevented plugging. After we made that change, we decided to see how it played out over the next couple weeks. And then here's a picture of that. So as you can see, there's a picture of some of the ammonium phosphate salts that formed. It was the reaction that we were looking for. Basically, we could tell that the ammonia was being attracted to that phosphoric acid more than the SO2. Unfortunately, as you can see there, with the lower acid injection rate, we weren't getting that rinsing factor as we did. You can see it in this slide. The picture on the left is when we were increased the flow rate of the acid injection, we were getting a really good rinsing effect, so you don't get the salt buildup as well, but that was burning through acid solution. The picture on the right shows our compromised solution where we embraced the salt buildup, as you can see here and on the picture on the right. And we removed some of the marbles of the inert media so that it allowed for more space for salts to build up. There was still rinsing that we noticed, so we did get rinsing of the salts, but this allowed, the marbles were originally at the top of the vessel. This allowed for more expansion just to further ensure that we didn't get plugging of the vessel. So if anything went wrong, lowering the marble level a couple inches gave us a little bit more of a headspace to fill with salts in case some issue occurred. But we still managed to keep that opening in the salt level where the acid injection was, and that allowed the sample to pass through and RADAs to be passed as well. So in conclusion, we were able to measure the low levels of SO2 despite high ammonia presence. We were able to play around with different methods or different amounts of acid injection, both to provide better rinsing if that's what the customer is looking for and less quarterly maintenance. It also allowed us to cut back on the acid dosing if the customer would prefer to use less acid. And it also allowed us to explore different non-traditional ways of scrubbing ammonia. And in future projects, we'd like to explore different ways of injecting the acid to get better, more even distribution for the future. Sorry, any questions? Sorry for going over.
Excellent job, excellent job. Any questions from the audience for Jeremy before we move on to the next speaker? All right, well, good. Thank you very much. And Jeremy, looking forward to working with you more. There you go.
Thank you.
All right. Now we'll prepare for the final speaker for the session. Seem to have lost the mouse. All right. Might need, yep. Oh. Either that or my bifocals failed me. Bear with this 1 sec. Or is it on me? Oh, there it is. It's way on the other screen. Thank you. I see that just as you arrive. Perfect timing on my part. All right. Okay. All right, excellent. All right, our final speaker for this session is Dave Windward from SICK AG. He's a good example of our industry where we just all kind of move around. Dave, I remember from the old Applied Automation Hartman and Brown days with the UK, so I've always learned be nice to your fellow compatriot in this industry. You never know. Anyway, he'll be talking today about enhanced mission monitoring from SRUs. A little bit about him. Since studying chemistry with German, David spent 30 years in the field of gas analysis, starting out with Hartman and Brown, followed by subsequent international roles for City Technology and Emerson. David joined SICK back in 2009, helping to establish the subsidiary offices in Turkey and India. In 2019, David took on the role of Global Industry Manager of Chemicals with a strong focus on refining, petrochemical, and fertilizer sectors. For hobbies, David is originally from the UK but lives in Prague with his wife and 3 children. He enjoys hiking, bird watching, gardening, is a passionate advocate for the environment, and is a founding member of the Prague Brentford Supporters Association. Woohoo! Oh, don't lose my mouse again. There we go. And let me get your presentation up here. And get you started here. There we go, sir. Well, thank you.
Okay, am I audible? Yes, I'm audible. Okay, so, good day. It's a pleasure to be here. It's my first, let's say, conference in the States, so it's been really interesting to see the nature of the conference here. I really, really like it. I think the fact that we're all here together, I think is a great thing. So I also want to congratulate the organizers for doing a great job. And yeah, it's a real pleasure that we come together as a community in this way. So fantastic. Okay, what I'd like to talk about today is a very kind of niche, specific application. It's emission monitoring from the sulfur recovery unit. So what we'll look at, and I've tried to give this a North American perspective. So we'll look at local regulations. We'll look at the application challenges for what I would describe as a pretty notorious emission monitoring application. And then what I would like to share with you is some information on a technology, a hot extractive infrared photometer. And then actually what we will do is we'll look at some data generated in a field trial from a refinery looking at this application, and then we'll wrap up. Okay, so in terms of the regulations in North America, and this is very interesting from my perspective, because on the one hand, you've got Subpart J, and Subpart J sets out a clearly defined emission limit value for SO2 of 250 ppms, and that refers actually to dry basis conditions, and it also defines that that's at 0 volume % oxygen. And of course, therefore, the regulation also requires an oxygen measurement, logically. There was also then an add-on, subpart JA, and that addresses the fact that for sulfur recovery units, oxygen enrichment has become very, very widespread. And of course, when you are working at enriched levels of oxygen, you're actually driving up your SO2 emission. So there's an element in the regulation that takes care of that. As you can see, the equation at the bottom, that simply sets an SO2 emission limit value according to your oxygen enrichment concentration. Now, if we look at the contrasting requirements from natural gas processing facilities, it's an entirely different approach, actually. So here, there is let's say, a description that, again, we have this thermal oxidizer, and behind the thermal oxidizer, the requirement here, in fact, it's not an emission limit value, it's a mass emission. And you can see that from the units required. So the SO2 emission rate as a sulfur mass flow in terms of kilograms per hour, pounds per hour. And it's really this contrast that I want to point out. So on the one hand, we have an emission limit value, and on the other hand, we have a mass emission. And they actually, therefore, place different requirements on the emission monitoring technology. So on the one hand, we need to measure, alongside our SO2 measurement, we will need to measure oxygen and potentially water vapor. Whereas for the mass emission, it's much more logical that we simply measure wet, if you like, and there are no additional components needed. So if we kind of wrap those two requirements up together, then what we really need is we need to measure the SO2 wet basis that gives us the mass emission, but we additionally also want to measure the oxygen and the water vapor. So that's really the demands coming from the regulations. What's now happening in the industry is that there's, at least from my experience, in the last year, 18 months, there's been a lot of talk about carbon capture from the sulfur recovery unit. And therefore, we should understand that there is a potential in future that CO2 is also going to be another component that is going to be of relevance and of interest to us when we're looking at this emission monitoring application. And being a greenhouse gas, CO2 is another gas that will be reported as a mass emission. So that's something that we might need to bear in mind for future requirements. Right, so much to, let's say, the regulations and to, let's say, trends in the industry. Let's now look at the fundamental reasons why this is such a difficult application. And actually, the graph that you can see, the blue trace is an SO2 measurement, the orange trace is a CO measurement, and the first point to make is that we get greatly fluctuating concentrations of SO2. So for the vast majority of the time, when the sulfur recovery efficiency is very high, we can expect to have correspondingly very low concentrations of SO2. But if your tail gas treater unit is out, then of course suddenly the SO2 can go through the roof, and that's actually what this blue trace shows us. In addition to that, the background gas gives us some further challenges. on the one hand, when the SO2 goes super high, we have a very, very potentially corrosive gas with a very, very high acid dew point. And equally, there's always the threat of having trace residual concentrations of elemental sulfur. And that is, let's say, for these two reasons, the idea that you would use a technology which is based on cooling the gas, for example, as a function to remove water vapor, that is something that brings an inherent risk with it, let's say like that. And we've got, of course, a very nice picture down below of an optical filter which has got elemental sulfur deposited on it because the temperature drops too low. So I would say that those are the three aspects that make this application particularly difficult. Let's now look at a technology in terms of how it might fit this application, and that is a hot extractive infrared measurement. And when we say hot extractive, the principle here is that from the sample probe, where we're extracting a sample, all the way down the heated sample line into the hot extractive analyzer, we keep that entire sampling chain at really an elevated temperature, something in the range 200 degrees C, which is 390 Fahrenheit. And the point being, we want to stay above the acid dew point. We also want to have what I would call a budget that we're comfortably above it. And also, we want to avoid any condensation and any potential for any residual traces of sulfur to be able to drop out and deposit either on optical parts or indeed in a sample system. What's also key here is that, therefore, because we have a heated system, we actually want to have as few interconnections as possible, which is why we really only have a probe, a heated line, and a hot analyzer. That's it. There's no filters, pumps, flow meters, and all the other, let's say, sampling elements that you get, for example, with a cold extractive design. For two reasons: the less interconnections we have, the less threat we have of a cold spot. And of course, the other benefit that we get with that is that we have a very, very simple system. It means that the maintenance requirements will be driven right down. So if we keep a simple design, the maintenance will be reduced. The other point that I should mention is the hot analyzer itself has integrally a heated ejector pump. In the old system, we used to have a good old membrane pump, which is fine, but that was a maintenance item. Okay, so now we have actually an ejector pump. So the way that the analyzer works, it's a filter photometer. I think it's a very, very well-known design for given applications. We use, for example, a dual wave principle. That's the basis for the measurement. So we will have, as you can see from at least, I hope you can see from the diagram, you have filter wheels. On those filter wheels, you'll have, for each measured component, you'll have a filter which is for the measurement wavelength, i.e. a wavelength at which the target gas does absorb infrared light, and then you have a reference wavelength at a wavelength at which your target gas does not absorb light, and therefore we want, for the reference measurement, we want to see 100% of the light intensity come through, and we compare that with the reduction in light intensity reaching the detector as a function of the pre-absorption of the light in the cell, thanks to the absorption by the target gas. And I think, I don't really want to get into this in a deep way, but what I do want to point out is that if you generate your reference and your measurement signals in the same pipe, then if we get some degree of contamination inside, some dust, maybe some contamination on the windows, whatever it might be, that's actually self-compensating. You'll get the same effect in terms of reduction of light reaching the detector, both on the reference measurement and on the reference and the measurement signals. And that is what makes this technology super, super robust. So to be quite honest, if you have applications here where there's a bit of dust flowing through the analyzer, we don't care, because it's self-compensating. And that's quite an unusual property, and that's what makes this analyzer super robust. It has a multi-component capability. As you can see from the table, those are the various infrared active gases that we're able to measure. There are some examples for measuring ranges. That's everything in milligrams. This is actually from the European approvals, but at least it gives you a flavor of what the analyzer is capable to measure. And key is, for this application, not only do we measure SO2, we also measure water vapor. We're also able to measure CO, NO, NO2, so we can cover the application in its entirety. Yeah, we're measuring in a raw, hot sample, so we're measuring wet, but with the water vapor measurement as well, that allows us to normalize dry basis as required by the regulation. But equally, because we're measuring wet, we can do the mass emission as well. So we can serve both of those regulatory requirements, whether it's an emission limit value, whether it's a mass emission, the analyzer will do both. There's one particular aspect of the analyzer design that really fits this application beautifully. And we should understand that when you configure an analyzer, you're configuring that analyzer, that optical analyzer, for a specific concentration task, let's call it. So if we're saying we want to measure 0 to 300 ppm, then according this Beer-Lambert law, where there is this relationship between the concentration and the length of the cell, so we say for this concentration, we have this length of a cell. And that's how we'll do it. So for a 0 to 300 ppm range, we'll have this length of cell. And with that defined path length, you actually have some restriction as to how flexible you can be in terms of either going to lower concentrations or higher. And I would define that the typical range ratio would be something in the range 1 to 10. It's difficult to get far beyond that. So if we're saying 0 to 300, we could add a range on that same path 0 to 3000, but beyond that, we're going to struggle. Okay? So, and for this application, as we've said, as we know, for the vast majority of the time, the SO2 is very, very low, but then suddenly we go through the roof. And the way that we address that challenge with this particular analyzer, we have 2 measurement filters for SO2. So where you see the large peak at about 7,500 nanometers, that large, strong absorption peak is for measuring our very low concentrations of SO2, because a large absorption peak gives us high sensitivity. And the way that we're then able to address the need to measure much higher concentrations is we actually use a completely different wavelength. So we have a second filter that's set up for about 4,000 nanometers, and that then gives us this flexibility and gets us away from this restriction of the ratios. So we use the big peak to measure, let's say, 0 to 300 ppms, but then if we need to measure 0 to 1.5%, then we can do that on the different wavelengths. So it really is a good fit for this particular application. So I want to come on now actually to share with you some data from a field trial. So we brought a new version of this hot extractive analyzer in 2018. We know this is a challenging application, so we really wanted to prove to ourselves and also to a customer where we were involved that yes, this is really fitting the application requirements. So what actually happened was there was an aging analyzer that needed to be replaced. This is on a refinery in Europe. And we provide a test system initially for the best part of a year. And you can see in the table, you can see the ranges that were set up. So we had this dual SO2 configuration, 0 to 300 and 0 to 5,000 ppm. And then there was the CO, the NOx, water vapor, CO2. Oh, and I forgot to mention, we also have an integrated zirconium cell to measure oxygen, because of course we need the oxygen measurement and we don't do that photometrically. So we have a zirconium that's doing the oxygen. And as I say, what we really wanted to do was we wanted to show ourselves that yes, we fit the application. And what we actually ended up doing, which I'll talk about, is we changed some ranges on the SO2 and on the CO. So firstly, a look at the sample system. Nothing here really out of the ordinary. It's a good old-fashioned sample probe with a heated sample line. What we did do is we had our service engineers go and check the condition of the filter up at the probe. And even actually on the bottom photo, please observe, even when you have two heated elements that are connected, you even there have a tiny cold spot, and you can see a minor amount of deposition of the elemental sulfur. So if you give it any chance, it's going to drop out, even between two heated elements. Of course, the amount of deposition we had there was insignificant, but it just reminds us of how key it is to stay hot. What we did based on our experience through the trial is actually we changed the range on the SO2 high. We understood that the 0 to 5,000 range was not going to cover it because we had a peak that went straight to 20 milliamps. So we actually extended the range to 0 to 15,000 ppm on the SO2 high. And we also saw some very interesting behavior on the CO, which I'll share with you. So we also doubled the range on the CO. And we decided to retrofit a methane channel, which I'll explain. So the first thing to point out is that we see actually quite a lot of fluctuations on a number of the components. So the orange trace is the CO. The light blue trace is the SO2 high. And so we saw a lot of, let's say, fluctuations. And I think that, again, emphasizes how important it is, for example, to measure the water vapor. Because if your water vapor is fluctuating, you really need that measurement to properly normalize your SO2 dry basis. The only thing I would want to say about the methane, we were not sure if the overall combustion in the thermal oxidizer was absolutely efficient. So that was actually why we retrofitted the methane, but there was no methane emission. So we can see that the thermal oxidizer does its job. What I'd like to dig into a little bit is this relationship between the SO2 and the CO. So what we saw was that this is the SO2 high. So what we would see was that the CO would be as it normally is, bumping it around a couple of hundred ppms maybe, and then suddenly when the SO2 goes through the roof, and this was going up to about 14,000 ppms, by the way, what's interesting to observe is that whilst that SO2 goes, the CO drops down to absolute zero. And then your SO2 drops off, and suddenly you get a spike of CO. Okay? The SO2 comes back again and drives the CO back down. And then when your SO2 kind of disappears permanent, let me say, then you get this massive spikes of CO. So we could see here really a clear relationship in the behavior between the SO2 and the CO. And we were wanting to understand what was going on here. So we consulted with the industry and some experts in the industry to ask them to interpret this. And they explained it as follows. They said that when your SO2 goes high, that is, of course, because suddenly you've got a slug of H2S hitting the thermal oxidizer, right? And when we're burning H2S, that's an exothermic reaction, so you're driving the temperature right up. And as you drive the temperature right up, your CO oxidation efficiency goes right up to 100%, which is why then, as your temperature, and by the way, this is the temperature trend that we then added. So you can see the effect, and it's about 50 degrees C between the two. So that's, well, it's a significant change. So the SO2 goes up, the temperature goes up, the CO oxidation efficiency goes right up, and then you get the reverse. When this slug of H2S coming through the thermal oxidizer disappears, then of course the temperature drops back down. And if the thermal oxidizer is not, let's say, really being controlled very efficiently, what you might get is a drop-off in the temperature, and then suddenly your CO oxidation is no longer efficient because the temperature's gone really down, and that is why suddenly you get this large spikes of CO coming through. So even though we just wanted to prove that, yes, we have a robust, reliable SEMS measurement, we actually were surprised to see some kind of elements where perhaps we're able to even contribute to a better control of the process here. Just to conclude, this is actually just a citation from the customer. So as I say, we set out to want to show that the technology fits the application. And this is really what the customer said. So both the trial analyzer, which run for a best part of a year, followed by the, let's say, the permanent installation, once we'd proven the capabilities, have proven themselves to be reliable, low maintenance, meeting application needs under all conditions. And I think that's another key point, because I do hear about, let's say, some idea that, you know, when the SO2 goes high, no, we're going to maybe switch a valve. We don't want to do that. But I think we have a duty of responsibility here. If we're a continuous emission monitoring analyzer, that means 24/7, and that means, in fact, when you've got these SO2 spikes that are a big contributor to the overall emission from that plant, we need to quantify those. So we can't be kind of putting the tin hat on and saying, no, don't want to measure it when it gets tough. We need to measure under all conditions. So that's really the summary. And I think this is, you know, for analyzers in general, it's really the application that demands the technology that's the best fit. There are in-situ analyzers out there, cold extractive, hot extractive, but fundamentally, it's really the application requirements that should guide us to what's the best fitting technology. And I think we've got a nice example here of an application that very, very well fits a hot extractive analyzer. We know it's a challenging application, and this technology is a good fit. It measures all the components we need, whether it's an emission limit value, whether it's a mass emission, and of course, if we've got CO2 as a greenhouse gas coming in future, then we're set up for that as well. That concludes the presentation. I appreciate your time for listening, and if there's one or two questions, it'd be my pleasure.
All right, do we have any questions for Dave? Oh, there we go, one there.
You said you added methane and measurement. Was the
Speaker, or?
No, thank you for the question. Yeah. So what you're able to do, because it's just two filters, so it's a measurement, the hardware side is not too much to be done. So what we did is we do a simulation in the factory, yeah, to get the kind of, that we can then provide the two filters together with kind of cross-interference tables, all the background information that allows that to be implemented on site. But it was done on site by the engineers. And of course, they take a test gas and check everything good, but it's done on site, supported by the factory.
Any additional questions?
Yeah, I understand. So you're talking about the MCS 200 here.
Yes.
We also have the 300. So my question is which applications would you recommend the 300? And did you do similar trials at other facilities with the 300?
Okay, thank you for the question. It would be a pleasure to talk on the booth if that would be possible, but let me give a very brief comparison. So this is an MCS 200, which is really an emission monitoring analyzer because we have a longer path length, and we achieve that longer path length with mirrors. The mirrors are coated with a special anti-corrosive layer, so they have a very, very long life. That's one of the things that we are very, very experienced in. So the MCS 200, I would say, is our standard solution for emission monitoring. It can, with the longer path length, get lower measuring ranges. But in terms of the SIU SEMS, the MCS 300 is viable. And what we can do with the 300 is we can actually go even higher on the temperature set point. So with the MCS 200, we're at 200 degrees C. If we need to go higher than that, we can go on the 300p, we can go to 230 degrees C. So we have had some applications in this part of the world where we've kind of been doing exactly that, kind of weighing up in terms of measuring ranges, in terms of acid dew point, which is the better fit. So those are the parameters that we play with, I would say, would be the measuring ranges and the acid dew point. Those are the two key elements that define if it's that one or it's that one. Does that answer the question?
And then just did you do some field trials with 300?
We've not done field trials with the 300p like we've done with this because the 200 was brought out relatively recently. But we do have references. We do have references. And of course, I actually think that the field trial of the 200 brings a degree of value to the 300p because they have, it's the same platform, right? It's the same platform.
Any additional questions?
Okay.
Excellent, excellent.
Thank
Thank
you.
you, Dave. Thank
My
you.
pleasure.
Okay, so we got to take it. And then it's over. Thank you, Doc. Yeah, this ends the session for the morning. We're a little early, yay. So I'm not sure if the vendors are ready for us yet, but we'll give them a surprise. And let's be back here at 1:15 to continue in the afternoon. Thank you very much.
They done messed up and gave me a microphone. Oh, hi. My name is Bobby Singh. I will be moderating session 7 today. We got 3 papers. Our first paper is, the name of it is a solution for trace level moisture measurement in challenging gaseous and liquid chemicals. The authors are Corentin Thierry and Josef Kraus. And I'd like to introduce you to our presenter, Cornton-Thierry.
Hello. Thanks, Bobby. So yeah, good afternoon, everyone. Hope you all had a good lunch. It was good. I liked it. So yeah, today we're going to be talking about trace moisture. It's, moisture is a difficult measurement. Moisture is always posing some challenge regardless of what you're measuring it in. But today we're going to address specifically the challenging part of what is already a challenging. It's just one thing. Can you reduce the reverb on the mic a little bit? Hello? Okay, I'll just lower it. Anyways, so yeah, we'll be addressing the challenging part of an already challenging measurement, which is, in this specific case, liquid and gaseous chemicals. What I'm going to do is briefly, why is it a challenging measurement, and which part of liquid and gaseous chemicals makes it, in a sense, even more challenging. Then I'm going to present a type of analyzer that is used for this type of measurements. It's a type of interferometer. I'll go over some applications that have been done using that technology, and then we'll look at a very specific case study. And I see all the people trickling in. That's great. It's something funny. I attended my first conference here 10, 12 years ago, something like that. And would sit in the back, look at the papers, and had you told me 10 years ago that you're presenting, I'd be like, oh, that's an interesting thought. So really thankful that we got the chance to present today and that I got the chance to see you all and talk with you. So before I go into that, I always ask a lot of questions. My colleagues are all smiling because they know that. And if I don't ask them right away, there's more that come, and I tend to forget my questions. So why I'm saying this is, if you have any questions, just interrupt me, raise your hand. We'll address them right away. Don't wait till the end. I don't want you to forget what you wanted to ask. It's totally fine. We'll address them as they go. So let's talk about moisture measurement. Moisture is present everywhere. It's present in the air we breathe. It's present in the water we drink. So you have water and moisture everywhere. And in our industry, in the majority of applications, we try to get rid of it. And this is in part a challenge because it's present in life everywhere, and we're trying to get to very, very low levels of not having moisture. And out of all the technologies that exist, they all have their pros and cons, but it doesn't change the inherent fact that because you have moisture everywhere, you have to kind of work around those challenges of how do I not get contamination, how do I don't get interference, and that is kind of the base reason why it can be so challenging to measure moisture. All of you that would have done it, validating moisture is also a similar issue. Now, when you get specifically into the chemicals, well, first of all, you have mixture of components. So some of them might interact one with the other. Some might have influence on how you measure moisture, giving a background. Certain chemicals happen to be corrosive, or they react with water to make very aggressive solutions. So then whatever analyzer instrument you're going to be using to measure moisture has to be able to withstand the corrosiveness. One other factor to take into account is, again, depending on the chemical, but you have risk of the very chemical reacting with itself and basically changing as you're trying to do measurements. So it is also something that can add a level of complexity. And then finally, as I mentioned a few minutes ago, when you're trying to do validation or to do a lab measurement to corroborate your values, well, some of those samples happen to be toxic or to pose a health threat. So even getting that sample and bringing it to the lab can pose challenges. And because of that, you might not be able to get a good validation, or you might not be able to get a good baseline for doing or for comparing your analyzer versus the lab. So I got here with me a probe that is a design that uses a Fabry-Perot interferometer. Yeah, that's a fancy name for it. It's just a type of interferometer. And this is the design we're going to be talking about today. This is the application case we're going to be reviewing with that specific type of measurement. The way it works, at the tip of the probe, I know you can't see it from here, but I'm just going to have to take my word for it. There's a small piece of glass. It's a special piece of glass. If you were to look at it, you're just going to have to take my word for it again. You can see some of the shiny surface. There is that, I call it a cake, because it's literally what it looks like. You can see on the electron microscope magnification those layers. You have that cake of glass that happens to be porous to water. The way it is being manufactured, it has tunnels in it, so moisture is able to penetrate inside that glass. And yeah, the specs are here, the size, what materials it's made with. But the core of it is that because it is porous to water, when that interferometer, that substrate, that cake, is inside a process where you have moisture, even at very, very low levels, well, that moisture will penetrate inside the glass depending on how much moisture you have in your process. So if you have a very dry process, or I should say if you have a drop in moisture in your process, basically you're taking water out of the glass. And if you have a wet process, if you have an upset, for example, and you have a slug of moisture coming through, you're going to be putting moisture into the glass. And this will change the refractive index of the glass. So what this technology uses is a fixed light source, which is an IR LED. Sorry. And you're continuously beaming light from a light source all the way to that interferometer and back. And basically, what I mentioned a few seconds ago, depending on the amount of moisture, your refractive index changes, so you have a wavelength shift in your original light source. And because of that, when you get your light back at the analyzer, you can just analyze the amount of shift you've had in your light. And from there, you can back calculate what the moisture is through, well, basically a calibration curve. When you would calibrate those type of analyzers, you're going to make multiple points at different levels of moisture and just allocate different wavelength shifts depending on the different moisture contents. So this is just examples. How would you mount such a probe in a process? Well, you can do an extractive sampling system. You can put it directly inside the process with an insertion probe. But basically what you want to do, whichever method you select, you want to make sure that one, the sample you will get is one representative, and two, the sample that you will get does not get impacted by whatever else might be going around it. And even for the measurement itself, we're talking about trace level moistures. We're talking low ppm or even sub ppm levels. So the coating that you're going to be using your tubing is very important, because absorption, desorption of the tubing with a day-night variation could be observed. Especially if you're measuring extremely low impact of pressure, impacts of flow. It's the joke we all make, like there's a problem with the analyzer, like, well, has your sampling system running? But it's really the core of it. Like you want to make sure that whatever you're designing, the sampling system will not be interfering with your measurement and will be enabling whatever technology you're using to measure it under the most real conditions possible. So that's what that Fabry-Perot interferometer technology, that's how we apply it. And that's how we make sure, basically, that the stream is properly represented and properly measured. Yeah, sales stuff. You can make wetted parts in Hastelloh. You can make wetted part in stainless steel. None of you are here for that. We have a booth downstairs. You can talk to us. We can go into a lot of details. What everyone is interested in is, what are the applications? How is this being used? So here I'm going to talk about two specific applications before getting into a real-life case study. So dry chlorine is a very common one we've been seeing a lot lately. So yeah, you have an electrolyzer, you make chlorine. Depending on the technology, depending on which part of the process you're measuring at, you're going to be looking at below 10 ppm. But again, chlorine is one of those challenging ones, because as soon as you start putting moisture with chlorine, then all of a sudden you have hydrochloric acid. And hydrochloric acid is going to chew up everything unless you have the right metallurgy. So, first thing to think about, exactly what I was saying earlier, when you want to be, if you're going to be, forgive my French, if you're going to be messing with chlorine, and I know it's happened to me a few weeks ago and didn't properly close a fitting and I just got a huge whiff of chlorine in the face. All of those things have to be taken into consideration when you're doing such analysis. And from both a safety, corrosiveness perspective, and of course, you want to break your line as little as possible, again, for a safety aspect, but also because you want a reliable measurement that you can count on for a lot of times to keep your line dry, to make sure that no corrosion is going to happen, or that, well, if you had a heat exchanger failure, if you had a membrane failure, that you can see the water coming through and starting to raise and destroy half your plant half the way if you don't take care of it. So chlorine has its own challenges. Chlorine is also very reactive. So the most common technology out there for moisture measurement, the aluminum oxide probes, don't really handle well with chlorine. Chlorine will chew it out. I know there's some ways of going around that, but it's still a challenge, and you don't have that many ways of going around it because of that very fact. Another one we've been looking at for quite some time now is butadiene in rubber production. So in a liquid stream, paper is about liquid and gaseous chemicals. And as I said, I don't want to make this a 2-hour sales pitch. It's of no one's interest. But in the liquid chemical world, you have a whole different set of issues because you have to take into consideration water saturation. So your liquids will retain different levels of moisture at different temperatures. And of course, all of this has to be accounted for whenever you're doing your measurement, especially if you're going to be directly in a liquid phase. I mean, yeah, you could always vaporize and measure a gas phase, but then it kind of becomes do I really want to be messing with vaporizers? And then in the case of liquid butadiene, from conversations with some other colleagues and customers, like, you run the risk of polymerizing as you're measuring, and you always have to take that into account and making sure that it doesn't interfere with your system. So those are just kind of examples of how this technology can be applied in 2 very specific cases. As I said, come down to our booth, we can have longer conversations, but that's just an introduction to give you an idea. And let's move into more of a real-life case study. So for confidentiality reasons, we could only share so much, I'll put it like that. So I'm just going to give a general overview of the process, and then I'll be here to answer your questions. But basically, for this specific application, we were looking at a chlorinated compound. So not chlorine specifically, but a compound that is chlorinated. What we found out is that whether it's chlorine or chlorinated compound, they're kind of treated the same, or you can use the same technologies to do one or the other, and they pose similar challenges to health, to corrosiveness, and to the actual measurement itself. In the case of you have interference, if you have like a changing background, when I'm thinking some applications might have some carbon TED coming through in and out. So this can throw off your measurements if you don't account for that. So the case of this specific application, it was a breakthrough measurement. So just making sure that you don't go above 5 ppm. It's an unstable compound, so pretty much as soon as you extract it, it starts reacting with ambient moisture, and it decomposes. And then finally, it's also toxic. So pulling a sample, quite challenging. You not just go there, pull a sample, go to the lab. There's an entire process. And in this specific case, the data I'm going to present, our customer ran in parallel a phosphorus pentoxide probe with our analyzers, and that's the results I'm going to be showing in a little bit. In the next slide, I'm going to be showing the sampling system, but just to give you an idea, we installed our probe into a heated sampling system with heated lines. We maintain it at 100 F38C. High flow rate to make sure that you have representative sample and your lag time is as little as possible. In the case of this specific application, we didn't have a lot of pressure. So the FabriPro interferometers are dew point analyzers at the beginning. So dew point analyzers like pressure. The more pressure you have, the lower you can read, because when you back calculate into ppm, it gives you a lower reading. So in this case, well, yeah, we didn't have a huge amount of pressure. Ideally, when we do those applications, we just say like bump it as high as you can, the more the better. And then again, because of the corrosiveness, because of the reactions that could happen and make subcomponents that were even more corrosive. All the wetted parts had to be either C276 or PTFE/PFA. PFA, I found out, I didn't know that, is quite challenging to find right now, so most of the parts were actually C276 Hastelloy type material. The sampling system that was used is a relatively simple sampling system. No disrespect to all the integrators, it's just the one we ended up using was not particularly complicated. We just had a flow controller, pressure regulator. We ended up having to add a back pressure regulator because that was discharging to a vacuum line, and we found out that it was pulling quite a lot of vacuum, so whenever you set the pressure regulator, you basically had vacuum after it. So back pressure regulator helps stabilize that pressure inside of the measuring cell. And then, again, because of the corrosiveness, that sampling system has a stream where you can inject air, purge it out before you open it, because I mean, whiff of fluorine in the face was no fun, but with chlorine in the data, I'd probably be 6 feet under, so we don't want that to happen. And then here are the results coming out. So what we observed, or what we and the customer observed, is that for some unknown reason, the phosphorus pentoxide only picked one upset, and I have a laser pointer here. I'm going to be pointing to that right side, so sorry for the folks on the right. You're going to have to look this way. So yeah, that was one of the interesting thing. The phosphorus pentoxide only picked that one upset, but this is when the analyzer got started, so it came from really, really high and just it dried down as it got into, we started flowing through it. But we're seeing those peaks here that are actually process-induced. And what was going on is there was a operator shift change. And basically, we even ourselves didn't understand it at first. And when we started talking with the customer, at some point we were chatting with one of the analyzer engineers like, oh yeah, it happens at this time of the day. Oh, that's our shift change. And so, you know, come to find out, because they ran it for a bit longer, and on the next shift this didn't happen. But come to find out that specific shift was doing something on their dryers, which was impacting the measurement, not by huge amounts, but it was impacting it sufficiently where you would have a little bit of shift, which the phosphorus pentoxide was not picking up, but our analyzer was able to pick up. I don't think they corrected it. I think they just marked it as an anomaly. But this is just to show the kind of responsiveness you can expect from such analyzer. And yeah, basically, the results over roughly 3 days of a continuous run for that. And I know this is short. I know I'm not getting into a lot of details. I'm hoping to get questions. If I don't, well, I'll just drink water, sit here. But now's the time for questions. Like if you're curious or if you want to know more, like how do we do it, why, where, when, like now's the time. So I'm opening it to you. Yeah, there's mics in the middle. So yeah, just.
Yeah, a couple quick
yes,
questions. Is it strictly vapor sample? I knew you said liquid butadiene, but I didn't know if you had to vaporize it or...
So in this application, the line was already a gas, so we didn't have to do anything. We were just sampling gas. So yes, so the type of technology you can use in liquid applications, it's what I was mentioning earlier. You just have to take into account now's not the right time to have a blank. Have to take into account the water solubility. Thank you. Water solubility curve to make sure that, because at different temperatures, the water solubility is different, and so how much relative moisture you can have in the stream is going to change. So that is something we would build it into our calibration to make sure it's accounted for.
Yeah,
yes.
and one other question is, since it's a porous space interaction, do you find any issues if there's like contaminants in there plugging the holes, or is that, or do you have to put like a sample system in front to make sure things don't happen?
You said amines? Did I hear you right? Did you say amines?
Since it's a porous base, it looks like something goes down a hole. I would imagine if that hole's plugged, that's probably not a happy thing.
So there are interference. CO2 is the most common one we see. It takes quite a lot, so usually you have to be above 10% CO2 for it to interfere with it. Most applications don't go quite that high. I'm not saying all, like I'm sure probably a lot of you are getting involved into carbon capture, so now we're starting to see more and more of those applications where we're looking like 90, 98%, 100% CO2. And yeah, it's something we're looking into, because in those higher ranges, it will create a lot of interferences, because it's not only that it plugs the pores, that some is able to make its way through, and then all of a sudden the sensor gets really confused.
Yeah, okay, thank you.
So CO2 would be one. The other big, it's an interferent because of the technology. It's going to be an interferent because of the chemistry behind it, but it's going to be like all your short chain alcohol or your ketones, because you start having H bonds, so the water has basically not enough pull from the probe to migrate into it. It just sticks to there. Again, we've done a bunch of tests, and what we found out is up until, depending on the actual component, but 2,000 to 5,000 ppm is still a safe range. So I'm thinking like if you have methanol carryover, or like if you have glycol carryover from your natural gas dryers, you're fine as long as you stay, again, depending on the component, 2,000 to 5,000 ppm. And then obviously no HF. So like when we do alky feeds, joke is not the right word, that's always the comment I make, like, well, I'm pretty sure if you have like in your alky feed HF coming back, you have bigger problems than that, but I'm still pointing it out. If you do have, for whatever reason, HF coming back, like it's gonna etch the glass and it's gonna melt a bunch of things, so no go.
Okay, thank you.
You're welcome. You, sir, yes, had a question too.
How do the dry down times compare to aluminum oxide?
It's going to be similar. So it's also an equilibrium device. So it's going to be comparable. Typically, what we say is T90 is anywhere from 15 to 30 minutes, depending on the process, and then the tail end is what's going to take a lot. And it's all based on a step change. So in most cases, in the process application, you're not all of a sudden going to be running 1 ppm and out of the blue you jump to 10. You normally have like a slow increase, especially as you start having a dryer breakthrough. And as that slow increase goes up, you can visualize it basically as infinitely small step changes as it goes up. And because of that, the analyzer just follows the process as it goes up. But for example, in the case of a validation, when you force like a 10 ppm stream, then yeah, you have to wait a little bit for the analyzer to catch up, for the equilibrium to happen. But as a reference, I would say, depending on the application, it's going to be similar, maybe a tad faster, sometimes a tad slower, but I would just consider it to be relatively similar. Anyone else?
Is there a pressure or temperature effect on the measurement that needs compensated?
I'm so sorry, Janardhan. Can you speak into the microphone so that everyone else can hear you?
Or temperature effect that needs to be compensated because the diffusion may change with pressure or temperature?
So we compensate for temperature variations within reason. So like, and you wouldn't know that. We had a case where we had quite a lot of shift from day to night, and it was throwing off the measurement. So if you have like a plus or minus 2-3 degrees, and let's just say Fahrenheit, 2-3 degrees Fahrenheit, you'll be fine. But if you're going to see a day to night of 20-30 degrees variation, like yeah, it's going to start throwing it off. So you can only compensate for like smaller ones, and once you have like larger temperature variations, especially as you go into the lower ppm or the sub ppm, you're going to have to use a heated sampling system that prevents basically that large variation in impact from the moisture. And on the pressure, no, we don't compensate. Well, so if you're doing dew point is insensitive to pressure. The analyzer itself doesn't necessarily care as long as you have relatively stable pressure, it's fine. But it becomes really important if you're doing like a ppm calculation because, as I mentioned originally, it's a dew point analyzer. And part of the back calculation involves inputting a pressure value. So if your sample or your stream is going to moving around a lot, or if you have, for example, back pressure, which is why I mentioned the vacuum, which is why I threw off the measurement in that case, because all of a sudden we were expecting, I don't know, like 12 pounds, 13 pounds, whatever, after the regulator, and the vacuum was pulling, like down to 1 pound. So what you have to do is either put in a fixed value to make your calculation, or the alternative is just plugging a pressure transmitter and live feed the pressure and have the system back calculate into ppm. There is some level of responsiveness, as in it's not instantaneous, whereas the pressure transducer is going to be like a quarter of a second, it updates the reading. The analyzer is going to take a minute before it goes through its cycles, does the update. So there's a tad bit of lag there as well. So that's also why we tend to recommend, if you expect like very big pressure swings, pressure regulators are going to help a lot with that. Anyone else? Thank you.
All right, for our next presentation, we had a little last minute change in presenters. The title of this paper is Coming to Consensus, How to Identify Bad Actors in the Oil and Gas Industry. Authors are Walter Last, and our new presenter is Anna Coulier.
Thank you, Bobby. Can you hear me okay? Yes. Thank you for attending this presentation. This presentation was supposed to be given by my colleague Wilfred Brink, but he got injured last minute. So now I have the honor, unexpected honor, to present his paper. So Wilfred, you owe me one. Okay, bad actors. Bad actors is a very hot topic at the moment in different industries, but what are bad actors? How important are the bad actors? And how can bad actors be identified? And most importantly, how can we convert bad actors into good actors? Depending on whom you ask, you will get different answers, because there is no standard procedure or checklist to follow. In general, bad actors are instruments that cause more problems than expected. But wouldn't be a better approach to identify or define what is a good actor? Because how can we know if something is wrong if we don't know when something is good? The problem with bad actors is that the definition of a bad actor can depend on whom you ask. If you ask me, I could say that George Clooney is a good actor. But maybe probably my motivation for saying that George Clooney is a good actor is very different from your motivation to consider somebody a good actor. So in the same way, people from maintenance can have a different criteria than an operator or manager. For example, that's why it's important to get a consensus across the board of what a good actor is supposed to be. With those criteria on paper, it becomes easier to identify what would be a bad actor. And once the bad actor criteria is defined, goals can be made for each instrument or group of instruments. The last step is to gather information to check if the goals that are proposed are achieved or if there are potential bad actors and how to handle them. To be able to understand what is being talked about, there needs to be an agreement on the terminology that is being used. For example, some key performance indicators are very straightforward, like uptime, frequency of failures, mean time between failures, but other KPIs are more complex, which need to be defined within your own context, like asset complexity and asset criticality. So, what is a good actor? Making an analogy with movie actors, good actors might be appreciated for their looks or their character, but do these qualities make them actually good actors? So what defines if an instrument is a good actor? Does that mean low cost or low maintenance or high precision, high reliability? And what is low and what is high? It is also important to look at the context. For example, a GC will come with higher maintenance costs than a probe, than a simple probe. But that doesn't mean that a GC is a worse actor than a probe. Bad actors. We can easily build consensus in defining bad actors as critical assets associated with frequent failures, unplanned downtime, and high maintenance overhead. And if the criteria for good actors is already defined, it makes it easier to define what is a good actor. A bad actor can represent a location where there is actually room for improvement, as the health status of closer equipment can be also revealed. This can lead to process improvement because, process improvement opportunities that might be overlooked otherwise. Which departments are involved in defining performance criteria? Are all their criteria necessary to determine a good actor? Are special circumstances applicable, like SEMS and safety equipment, and should they all follow the same criteria? These are all questions that we need to ask. Perfection is too expensive, but doing nothing, it's also too expensive. What is an acceptable and feasible performance target? The design of a plant of process might work on paper, but after commissioning, the reality might not always match the assumptions made during the design phase. That is why it is important to understand the system based on real data that is being gathered over time and adjust accordingly when needed. Simple instruments don't need the same criteria and effort than more complex or expensive instruments. With today's technology, it's possible to gather real-time data from an instrument and look back at the history of that information to monitor how an instrument is performing. Another point very important, and this is based on our experience, is the collaboration. collaboration closely with if you have an asset management system, if you collaborate with your vendor, the right tools can be developed and implemented for an easier identification and analysis of bad actors. How to analyze actors? Visual inspections are powerful, but very time-consuming and only provide limited insight into the equipment. Continuous data gathering provides an overview of what has happened to an instrument over a period of time before heading out for routine maintenance. With the availability of the instrument history, maintenance decisions can be improved. A computer excels at gathering data, large amounts of data, and processing this data. But it's not that good at being creative and solving problems that have happened before. On the other hand, a human is slow in working through large amounts of data, but excels at solving problems and creating solutions. So why don't combine both strengths? Let the computer deal with the processing of large amounts of data, and let the human do complex decision making. It is also important not to gather all the information that is available in a situation, because it can be overwhelming. Instead, try to identify a critical mass of data that will be enough to determine if the instrument is performing as expected or if extra action is needed. Anyway, you would like the system to remain useful. Well, this picture has a double meaning. It could be throw away money due to bad actors, or grab lost money out of the bin by turning bad actors into good actors. The consequences of asset failures can range from bad reading to a plant shutdown. An asset that measures the quantity and quality of a product before the product is delivered to the customer will cause a loss of profit when it's unavailable. Also, an asset accountable for safety will cause shutdowns if it does not perform well. For these reasons, it is critical to identify if an asset is a bad actor or not. It is also important to look further than a data point. When an instrument measurement is communicated, it is important to make sure that the data is of good quality by comparing it with other measurements from the same equipment or unit, for instance. By doing this process, deviations can be noticed and corrected before becoming actually problems. Combining success factors like availability and reliability rates can provide a good indicator if an asset is a good actor or not. For example, setting the availability rate threshold at 90% and the reliability at 85% will provide a list of those assets that need more time and resources to turn them into good actors. But here is where your knowledge is needed. So the asset management vendor can make and implement smart algorithms to determine this, but your input is crucial in this process. This is a drawing, I don't know if it's good to see, about the workflow in the plant. For instance, you go to the plant and make a visual inspection of one of your analyzers. And looking at the top left graphic, the first thing you do is to make some data acquisition of your equipment. Then you need to process this data, make some analysis that can cost time, and then you will determine the health status of your equipment. If the health status is okay, then yeah, we move to the top right graphic. And well, nothing happens. You can continue and move forward to the next equipment. But if the health status is not okay, then we move to the below graphic. And you will need to diagnose the fault, make a prognosis, and eventually make a maintenance decision. And then it will be corrected and confirmed if the solution was okay. So the idea is to automate a great part of this workflow. If we can let the computer or the system do the process shown on the graphic on the top left, then you can use the time spent by the engineers can be better used to look at the root causes of the problems. When the root cause of such a problem is found, that can be used to create triggers to prevent the same problem from happening again. So this knowledge will be fed into the system, and he will provide alarms or events before the same issue happens again. This gradual process can leverage the knowledge of more experienced personnel to less experienced people. Engineers can focus on why problems occurred, while technicians can implement the fixes. The engineers can use that information to fine-tune the observation process, and then, as I said before, to feed the system with this information. So the accurate identification of bad actors depends on monitoring ahead of time, looking forward and not backward. By monitoring success factors instead of failures, intervention can be done by making adjustments before an asset becomes a failure. It may seem like a big leap, but stopping the habit of running equipment until it breaks can prevent breaks from occurring in a more efficient way. So this is what we wanted to tell you. Yeah, if you would like more information, you can visit us at our booth. Are there any questions? So thank you very much.
I can hear myself. That's good.
Last but not least, our last paper for this session is titled Pain Points of Process Organics Monitoring and How to Overcome Them. Author is Walter Last, and wait, I'm sorry. Sorry. Authors are Amanda Tyndall and Sage Mosteller, and our presenter is Amanda Tyndall. Thank you.
Thank you so much. How's everyone doing this afternoon? Good? Everybody awake after lunch? All right. I'll try to keep myself awake, keep you awake. I flew in from Colorado this morning, so I'm like, wait, how many hours have I been up so far? Almost 12. Good day so far. All right, well, thank you everybody for sticking around. Really excited to give this talk, and it kind of builds on the last one. I've really enjoyed the session so far today. So we're gonna talk about process monitoring, and really my goal here is to have you think about what pain points I'm sharing, think about what other pain points you see. We'll talk about applications, and then we'll go through some new developments that are trying to overcome those pain points. But again, open to discussion afterwards, and really just wanna kinda take a step back and think about what our goals are. So we'll start with an introduction to kind of process monitoring. What are we really trying to do here? What are our goals? And then why would we be monitoring organics? So we're gonna talk about total organic carbon, we're gonna talk about volatile organic carbon, what the different types of things that we're actually measuring, and then how we're measuring them. Then I'll highlight 3 pain points that we've seen, but this is not a comprehensive list. So I encourage you to think about other ones or challenge me on these. And through that, we'll show some opportunities for improvements. So as we begin, again, I just kind of want to zoom out a little bit and think about, all right, we're going to talk in this session about some parameters. So looking at total organic carbon, but also what's the difference between that and inorganic carbon and volatile organic carbon. These are different types of measurements. Some can be with different instruments, some can be within the same instrument. Sometimes we're looking at specific compounds. And so there's a difference between that sum parameter and that specific contaminant. And those each have different purposes that they serve. Then when we think about monitoring, well, what are some of the challenges and things that we have to do with all instruments? Well, we have to maintain them, and then we have to make sure they're calibrated, or that they're verified, or that they're validated. We have to think about what could be automated. How long can I step away from this analyzer and still trust it? And is the data that's coming to my system reliable? Is that good over time? What is that time period? And when do I then have to go back and do some maintenance or change out some consumables? Then we'll look at versatility. So can one unit do multiple things, or is one unit really specific to this niche application? And then what's the responsiveness of it? The goal really is to look at how do things change and how fast do they change. So can we detect that change with this instrument? And so we're going to talk about applications from river to river is one way we like to think about it. When water comes into a process, it's coming from the environment with some level of contamination. It's treated, then it's used for certain purposes throughout that process, and it's discharged back to that environment. So kind of from river all the way through back to river. I'll just give a quick introduction and definition of what TOC is. I know many of you are probably very familiar with it, but if we look at the bottom here, it's defined by the EPA as the gross amount of organic matter found in natural water, including suspended particulate, colloidal, and dissolved organic matter. But we're looking at natural organic matter, solvents, microbes and bacteria, or the sugar and food for microbial growth, pharmaceutical compounds, food and beverage, ingredients, so flavors, dyes, proteins, starches, resin leaching, polluted condensate, effluents. So all of these things have organic components to them. Those can be simple organic molecules, they can be complex, they can be polymers, they can be combined with complexes of metal, halogens, you name it. So we're looking at all of these together in one group, and the way that then those are measured is they are oxidized and measuring that resulting CO2. So that's just a kind of brief introduction to organics monitoring. And so what would this look like within an industrial process? Well, it could be from the source water, maybe something that passes through that source water treatment. Could be some leaching off of an ion exchange resin or maybe the resin itself has some organic components to it. Might be organic halogen compounds or nitrogen compounds that are complex together, and maybe we can't measure those with conductivity in the source water, but maybe then in a boiler system those break down and reveal other ions, or they maybe depress the pH. Could be even lubricating oils or degreasing solvents. So as we look through this list, all of these have organic components to them and would be included in that sum parameter. So when we think about why are we using it, these are some of the reasons and some of the things that we might be wanting to detect. Coming back to that environmental water that comes in. Water comes in from some source and it's going to carry a level of contamination. Wherever you start from, that's your baseline. And then that has to be treated to be used for whatever process it's going to be used for. So thinking about some of these different components then later helps us analyze, well, what tool would be good to measure all of these? And what are we picking up or not picking up? So I show here, humic acids are one that come from the environment. These are complex molecules with many rings. Or we have simple things like sugars. We have polysaccharides that might be longer but flat chain. We have some that are bound to chlorine, maybe things like chloroform. We have urea, other nitrogen organic compounds. And so, amines, organic acids, these are some of the different types that could cause problems in certain parts of the process. They could maybe lead to equipment degradation. They could maybe lead to leaks from the process side into the product. So as we think about, each of your processes or what you're responsible for, what are the contaminants of concern and how can we then best address them with the right analytical tool? If not, the goal isn't just to monitor for monitor's sake. The goal is to analyze these samples so that we can prevent downtime, we can prevent damage, and optimize profits. So our goal is always to make more revenue and minimize costs. Well, what could happen if we don't monitor and we miss a leak? It might be asset degradation over time. Maybe we don't realize it for a while and then the equipment just starts to degrade. Or it could be something very sharp that we have a large leak and now the process has to be shut down immediately. Or there are things in between. You could have heat exchange capabilities that start to slow down because of contamination. We could need higher blowdown rates. So there's your short acute problem, there's your chronic problem, and then there's many in between. This is kind of a diagram of what I was mentioning from river to river. So when we think about where we want to monitor and the critical point, it's going to vary depending on what the process is and what the current challenge is. So when water comes in, maybe it's that source water treatment. Maybe we're having a hard time because organics are coming in and fouling that pretreatment or reverse osmosis membranes. Then usually the water kind of travels and it's used to make steam. A lot of times that helps drive these processes, and that boiler feed water has to be very pure, free of all contaminants, or else it can degrade that equipment and cause corrosion, deposition, or scaling. Then maybe that water is used in the process itself. So what kind of level of purity or quality does that have to be at? And each of these, there's a fit for purpose quality. Not all points need very pure, nice, lovely water. Some points it just needs to be good enough, or we need to remove down to this level of contamination. All of that then eventually generates whatever wastewater is going to be treated and goes back to the environment. Sometimes it might be multiple locations that the wastewater is coming back to that then we need to see how does that change over time. Is one party loading more? Is one party loading less? And now my concentration is off? And then how does that affect the wastewater treatment before it's being discharged back to the environment? So each of these points might not all need to be monitored for organics, but sometimes there's a critical point where that quality is suffering and needs to be addressed. The four main ones that I just mentioned were kind of your source water coming in, that utility water, whether it's used in the process or used as an ingredient itself, and then the wastewater. So what could be some of the reasons that we monitor here? Well, maybe real-time detection of source water changes, as that changes with a storm, with an event, maybe downstream of another facility. And then on the utility water side, how can we do that to make the pure boiler feed water without any contamination or any leaks? We did a study a couple years ago where there were some bad seals in boiler feed water pumps that started to leak glycol, and they didn't realize that until it had caused a depressed pH within the high temperatures and pressures. When we think about it in water as an ingredient or in the process, how does that protect the product itself, and how do we avoid any cross-contamination when we're moving from one product to the next? So each of these kind of give a reason for why we'd want to monitor at certain locations. Looking at that steam cycle and cooling is one of the most important applications. So we'll go through a little bit more detail on that utility water side and then also on the wastewater side. But we're going through many different treatment steps, and as we go through multiple treatment steps, that's expensive. You know, RO systems are expensive, ion exchange systems are expensive. How do we optimize those to remove the level of contamination that we're expecting, but also make sure that those assets are protected and they're healthy and they're living their full, long lifetime? Another application that I haven't mentioned as much is when we make that steam, then sometimes we try and return that, or we try and condense it back down and polish it so that we can reuse it on site. So how can we prevent any liquid leaks or process leaks of things like glycol or other cooling fluids that could cause contamination to be recirculated through the process? On the wastewater side, as I mentioned, when we think about it, there's kind of three main stages. There's what's coming into the process, how's that treatment working, and then what's going out. A lot of times we only think about what's going out. Am I meeting my discharge compliance? And if we're just looking there, then we're not seeing how the process is actually working. And maybe the process is degraded because that influent loading is so variable, either in load or in concentration or both, that it affects the nutrient balancing or the treatment equipment itself that's trying to do all of that work. A lot of times we just kind of shove wastewater off and we say, yeah, it's good, we're dealing with it, no problem. But once you hit that point where the discharge isn't in compliance, then that's when you really need to think more upstream of what's coming into that wastewater treatment. So that's kind of our introduction to process monitoring, to organics monitoring. Now we'll start to move into what are some of the pain points of analytical instrumentation in this space. When we think about process monitoring, our goals, the way that I kind of try to sum it up here is we're trying to establish a baseline. Where do we normally sit? Okay, once we have that, if we have a stable baseline, now how do we detect a change in that? That's our goal, is to be able to see any deviation from our normal process conditions. Once we detect that change, then what's the severity of that? And now how can I go take action? Take a corrective action, make a decision. That's what we're trying to do with analytical instrumentation, is we're trying to know what that baseline is, detect that change, and then make a process decision. So through those three steps is what we're taking into context as we look at these next pain points. And again, I'm just mentioning three here. You could argue those, you could have different ones open to that discussion. With these top 3 points in mind, we're trying to save money, save time, save labor, catch a process upset, and then improve over time. The 3 that we've come up with here that we want to discuss further are 1, not being able to detect the contamination of concern. So when we're trying to figure out, can I detect that glycol leak? Well, what's the right tool for detecting that? Or how can I detect, that contaminant from the source water that maybe I wasn't picking up before? So you have to be able to detect what you're looking for. Number 2, you have to be able to detect that within a timely manner before it harms equipment, processes, or causes any downtime or unwanted repairs. If you can't detect it in the proper time frame, it's not useful to then take that corrective action. And then finally, the one that I think everybody's familiar with and concerned about is if the analyzer or equipment is down for maintenance, there's no way it's giving any data to make any kind of process change, upset, or decision after that. So the instrument has to be detecting what we're looking for, gather that in the right amount of time, and actually be working and processing uptime. So now, number one, fully detecting the contamination. We started at the beginning talking about organics monitoring, as a sum parameter versus a specific parameter. And there are reasons and uses for both. When we're trying to measure many different compounds and look at that gross contamination, sometimes that's easier to use. When we're looking for one thing and one thing only specifically, then a specific analyte is important. And so what are the things to think about here? Well, time, of course. How long does that measurement take? What sensitivity are we looking at? Are we looking for really, really clean? Or are we looking for just, hey, it's moderate, I'm good, okay, great. What's the accuracy? What's the range that it can handle? Are there gonna be large spikes? And then is it picking up those key things that it should be? And even among TOC technologies, there's a wide variety of methods. So it's important to understand two things here. What is being measured and how is it being measured? So first, the what is being measured. And I'm sure many of you are familiar with this type of chart, but when we think about carbon and organics, this table kind of describes the different forms. And so you might be more familiar talking about NPOC or DOC. So now let's do a quick definition of what these are. Total carbon, all carbon species in there, everything at once. Well, that splits off, and we have total inorganic carbon and total organic carbon. So TOC is that total organic carbon piece, separate from the total inorganic carbon. Well, what is total inorganic carbon? It's that background CO2, carbonate, bicarbonate. Those species are often measured differently, or they're removed from the sample because they're not the ones that are reacting and causing spikes or damaging equipment. Now, sometimes we want to measure CO2 alone. Great, we can do that. When we look at total organic carbon, that can be broken down into non-purgeable organic carbon and purgeable organic carbon. Now, I'm saying purgeable organic carbon, not necessarily volatile organic carbon, because there is some slight difference there depending on how much certain compounds want to leave water and then how much they want to be outside of that and purged off if there's gas coming in. Non-purgeable organic carbon can then even further be broken down into dissolved organic carbon and colloidal or particulate organic carbon. Dissolved organic carbon is only that amount filtered through 0.45 microns. Now, the human eye can see down to about 50 or 60 microns. So that's 2 orders of magnitude difference to what the human eye can see. So a lot of times people throw out different terms. Just wanted to take a quick moment to discuss what is being measured when we talk about organics monitoring and total organic carbon analyzers. So when we talk about measuring TOC, that would include NPOC and the purgeable organic carbon. And there's a lot on this slide, but it just shows there are many different TOC technologies out there. And it all depends on what's fit for that purpose. So if you're measuring very, very pure water, essentially you're looking to detect nothing. That's the goal. And if you want to detect something very small, okay, there's a small spike there. So you're looking for good sensitivity, you're looking for good accuracy. On the other hand, if we're measuring wastewaters, the technology is going to be more complex because we're going to need to handle complex environments often, extra contaminants, salts, stickiness, oils. And so there's this range between pure and complex where, yes, the level of maintenance goes up with the more complex the sample, the amount of time it takes to make sure that instrument's running goes up, because we're looking for a lot in the sample versus looking for nothing in the sample. So this chart, which is outlined more in the paper, kind of talks about where each technology is used for different applications, whether that's drinking water, wastewater, utility water, and also if it's available in a lab or online or both, if it complies with standard methods, and what the oxidation technology is and the detection technology. We'll just hone in on one subsection of this and talk about combustion TOC. When we think about combustion in our minds, it does kind of make sense that that is oxidizing everything in the sample. Okay, great. Well, now how does that work? There are two different types of combustion for TOC technology. There's catalytic combustion up to a certain temperature, usually lower temperatures, and then non-catalytic combustion at a higher temperature, usually above the melting point of salts. So within those two types, one with catalyst, one without, when we use a catalyst, that catalyst is acting to aid the oxidation process. So over time, the active sites on that catalyst start to be taken up. And over time, it might require more calibration frequency in order to maintain the level of oxidation that's maximal. In addition, there could be different oxidation capabilities and oxidation levels for different types of compounds. So a catalyst site might be taken up more by a complex carbon compound that needs to be broken down versus a less complex carbon compound. On the high temperature non-catalytic combustion, that really gives a true sense of complete oxidation because there are no catalysts, there is no degradation of that catalyst, no active sites that go to it, so the accuracy and the stability can last for a longer amount of time without as many changeouts of consumables or different calibrations. So just a quick comparison between kind of catalytic and non-catalytic combustion of the overall types of TOC analysis. So that was number one. That was, are we detecting what we need to? Are we detecting everything that we need to? Number two is, are we detecting that in the amount of time that we need to? Sometimes data takes days, sometimes it takes hours. You know, BOD takes 5 days, chemical oxygen demand, COD takes a couple hours. TOC you can usually get in a matter of minutes, so usually that's not an issue. But sometimes we might need even something faster than that, because we're trying to detect a leak. So depending on what the application is, if time is important, it's important to look for a tool that can provide a result in the amount of time that you need to before you need to take that process change. So this is a graph kind of showing what some newer instruments are doing where you can actually try to predict what the end value would be. So one way to do that would be taking a look at the early slope when we're detecting organics, and then take that and extrapolate it and predict what the final result would be to know, is that within my alert limit or is that above my alert limit? And it's above, then maybe I need to switch this stream and change it and go forward. So some of those things give us an idea of how can we make these improvements. And I've just gone over some of this, but in addition to kind of that predictive nature, having newer, better data management allows us to know more than just the data itself, but also how the analytical equipment is performing. So are we getting an idea of what's happening within the sensors of the analyzer, what's happening with the consumables? Am I making sure that everything's 100%? And that way I don't have to worry about trusting the data because the instrument's self-diagnosing, helping itself to learn what's going on within it so that we can either make an update, make a change, or know that everything's going fine. One last thing on this point is to consider what's happening within the analytical tool. So when we break down the different steps of monitoring TOC, some things to consider. Time, we just mentioned, the complexity of the analytical steps, if there are reagents used, what kind of consumables are needed. And a lot of these will be evaluated whenever somebody's going to purchase a new equipment or a new set of analyzers, but just some things written down here so that you can evaluate those. Is there troubleshooting that's easy? Are there moving parts that might fail? Are there new automation or predictive features like I was just mentioning? And then as we go through each of these steps, every TOC analyzer goes through these steps. We're preparing the sample. First, we're handling the sample. Is it complex to handle? Are there a lot of particulates? Do we need to do any filtration? Do we need to heat or cool it? Then we prepare that sample, mixing it with whatever reagents or not that it needs, oxidizing it, and then separating that gas and liquid to measure that final CO2. So just some things, again, to consider as we're thinking about process steps and we're thinking about what equipment to use or not to use. Well, when it comes to time, looking at what's happening within the analyzer is important as well. And then last but not least, Is there high maintenance involved with the analyzer that's causing it to be down, in which case we can't detect the change and we can't make the corrective action. So instruments are really only useful when they're working properly. If they're not working properly, we're not actually getting any data from them. So it's important to know what are the maintenance tasks, how complex are they, what consumables need to be changed out, are those complex, or are they off the shelf? Are they easy to use? Is it buying this list of parts, or is it cleaning out some sample lines and tubing? Depends on what people favor, what equipment they have, and what types of challenges they want ahead of them or not. So some improvements that have been made in some newer analyzers are looking at really keeping things modular. So keeping all the components separate so that you don't have to go in and take and replace the whole analyzer if something goes wrong. You can replace one small component. Or you can get components that are off the shelf, so maybe they're really easy or inexpensive to replace out. And then the predictive part is really important. So is the analyzer smart enough to learn, okay, is this starting to be used more often than it should? Well, why? Is there a leak, or is there a plug, and how can we then prevent that from happening? But if we have that insight from sensors on board, maybe we can take decisions before the instrument's down and before there's a need for extra maintenance. So here are some images of how something could be modular. I'm just going to try to exit out of that. And a screen of what a predictive maintenance screen would look like. So are we 100% on all our consumables? Are some being used up? And is there any maintenance task that needs to be done? So to start to wrap up a little bit, what we talked about today was we talked about industrial process monitoring, what the goals are of that, to establish a baseline, to detect a change, and then take a corrective action, with ultimately the goal to drive quality, to drive control, and compliance. We looked at organics monitoring, what is being measured with TOC, how it's being measured, and how that can accurately and reliably capture contaminants of concern, either organic halogen compounds, solvents, source water contaminants, all of those organics that are coming in and maybe being added or removed from different process units. We identified 3 main pain points being, are we detecting what we're looking to detect? Are we detecting that in the matter of time that we want to? And do we have high maintenance, or are we able to actually have high uptime? Which one of those? So some of these can be overcome with some of the following notes. Maybe units have predictive maintenance or onboard sensors to try and minimize that downtime and maximize uptime. Are the consumables easy? Are they inexpensive? Those are always important to evaluate over the lifetime of an analyzer. Is the design simple? And is the process of actually analyzing the contaminants, is that something that we can understand, or are there a lot of complex steps and different reagents involved that could cause problems with certain samples? And then there are automated features. So maybe we are more hands-off, and the unit can do self-diagnostics, self-calibration. That kind of helps because then there's less hands-on time, there's less downtime with the unit. Some other features that can help with complex samples are things like rinsing, automated maybe even, or rinsing between a tough stream and an easy stream, and the ability to handle particulates that could sometimes clog up different analyzers. And then last but not least, is there the flexibility in case there is a change in the process? Can a unit adapt to that, and can it be versatile enough to maybe measure not only TOC, but TOC and VOC, or be able to look at the IC amount? So just really appreciate the time here, and I'll take any questions or discussion if people have other ideas. All right, if not, thank you so much.
Thanks for attending, everyone, and that concludes our session.
Moderator, The first talk is multi-parameter natural gas quality analysis using tunable dye laser spectroscopy. The speaker is David Haight. David is the Vice President of Product Innovation of Galvanic Applied Sciences. He has BS degree in chemistry from University of Calgary. He has 30 years of experience in the online analyzer world. He has held several positions within Galvanic Applied Science. During that time, including application development, field service, and support, training, manufacturing, product development, and commercialization. His hobby is golfing, cycling, and playing guitar. Now, David.
Thank you, G. And thank you, everyone. Thanks, everyone, for sticking it out to the last session of the day. And I'd like to offer a special thank you to the committee of the Analyzer Technology Conference for allowing me the opportunity to present on this topic. It's multi-parameter natural gas quality analysis using tunable diode laser spectroscopy, which is kind of a mouthful. So from this point forward, I'll be referring to that as TDLAS, and I'll hope that everyone understands what I mean by that. So by way of context, talk a little bit about natural gas quality measurement in general and what some of those requirements are. We'll do a little introduction, or for many of you, I'm sure it will be a review of tunable or TDLAS in general. And then I'll go on to describe some techniques that we've developed to be able to measure multiple components in a single analyzer using this technique. Discuss some testing that we did and some performance of the system, and then wrap things up with a little brief summary. So gas quality measurement in general. So we see the demand for natural gas is continuing to increase as the world moves towards either decarbonization or lower carbon fuels. And there's two sort of macro trends that we see going on. One is the export of natural gas from North America. I think the US became a net exporter of natural gas around 2016 or so, but according to the Federal Energy Regulatory Commission, or FERC here in the US, 8 operating liquefied natural gas plants in operation, currently 5 approved and under construction, 11 more approved, but not yet under construction. So we see that demand for not only domestic use, but also for export increasing. The second trend that we're seeing is a lot of alternate sources of natural gas coming online, specifically renewable natural gas from landfill waste, for example, wastewater, agricultural waste. Currently in North America, there's somewhere around 200 renewable natural gas plants in operation, another under construction. And a significant number of these plants actually have tie-ins to the natural gas infrastructure, so they're actually injecting their product into transmission pipelines. So gas quality measurement is typically governed by a tariff agreement between a seller and a buyer of gas. This can happen typically from a processing plant to a transmission pipeline, from between transmission pipelines, from transmission to distribution. There are several key measurements that are being made at this time. The first being gas composition, which is typically done by a gas chromatograph. From that composition, of course, physical properties such as heating value, specific gravity, Wabi index, these sorts of things can be calculated. But there's also several key impurities in the gas that are monitored and have limits on how much of each of those can be injected into the pipeline or transferred during that custody transfer transaction. And specifically, 3 of these are hydrogen sulfide, carbon dioxide, and water vapor. So in the conventional natural gas value chain, typically we're bringing raw gas out of the ground, either from a gas well or possibly associated with some oil. It goes into a processing plant, typically liquids and hydrogen sulfide if it's sour gas. These things will be removed. And the residual gas that's left over, we usually refer to as sales gas, and that's what's injected into typically a transmission system. And from there, it's carried all over North America to either its end use or
possibly into storage. It can go into a distribution system. It could go to one of these LNG liquefaction terminals that I mentioned. But at essentially every place where that natural gas changes custody, there is a gas quality measurement point. And as we see, as that demand goes up, we see more and more tie-ins. Also, as we see renewables becoming more prevalent, we also see more tie-ins. So gas quality measurement is becoming more important than ever before. So in the renewable natural gas value chain, again, we're taking waste, typically agricultural waste, wastewater, those sorts of things. It's turned into biogas, which is basically just the raw product from the anaerobic digestion of that waste. Sometimes that product is used right at site for either heat or electricity, but it can be further refined into biomethane. And that biomethane can also be injected into the natural gas transmission systems, and there is typically a gas quality measurement point at that point as well. So circling back to those three key impurities, hydrogen sulfide, carbon dioxide, and water vapor, typical tariff limits in North America for hydrogen sulfide range anywhere from 4 up to 16 ppm. You may hear this expressed in alternate units of grains per 100 cubic feet, and that corresponds to a quarter grain up to 1 grain. For carbon dioxide, typical tariff limits are 1 to 3%. For water vapor, typical tariff limits range anywhere from 90 to 100 ppm. Again, you may hear alternate units for water vapor in pounds of water per million cubic feet of gas, and that would correspond to 4 to 7 pounds per million. So these are all of interest, typically because they are contributors to corrosion in natural gas infrastructure. So they are limited, and the amount of these components that can be transported in natural gas, again, are limited and governed by tariff agreements. So all three of these gases are good candidates to be measured by tunable diode laser spectroscopy, or TDLAS. I'll just do a quick review of some of the basics here, but the basics of the measurement rely on exploiting the vibrational and rotational modes of simple triatomic or quadratomic molecules. So for example, on the screen here shown is CO2. So it can stretch, rotate, vibrate, and have all these different movements. And these movements, or vibrational and rotational modes, are quantized. So that means that they only happen at very specific frequencies. So if you could irradiate those molecules with a light source that corresponds exactly to that frequency, that molecule will absorb some of that light. And using the Beer-Lambert law, we can relate the absorbance of that light to the concentration of the molecule that we're trying to measure. So these are absorbance profiles of the gases that we're interested in measuring. So the top one is CO2. The red lines, 2 down, are for water vapor, and the blue ones at the bottom are for H2S. I've also included here the absorbance profile of methane, which we may not necessarily be interested in measuring, but it is the main component of natural gas, of course, so we have to certainly be aware of its presence. So again, each one of the lines that you see on these graphs do correspond to a frequency of some rotational or vibrational mode of each of those molecules. So circling back to the Beer-Lambert law, we know that if we put gas in a cell that has a fixed length, if we irradiate it with light, and we can measure the intensity of the light going into the cell, we can measure the intensity of the light coming out of the cell. And by calculating the log of the intensity of the incident light over the intensity of the exiting light, we can measure a value called absorbance. And absorbance by Beer-Lambert law is equal to the molar absorptivity coefficient, which is just simply a coefficient that is an inherent property of that molecule. It kind of defines the amount or strength of the amount of energy that will be absorbed by that molecule. We know the length of the cell, and then the concentration. So if we rearrange Beer-Lambert, we know that concentration will be equal to the absorbance divided by the molar absorptivity coefficient times the length of the cell. So the tunable diode laser itself make very good spectroscopy interrogation sources. They emit very narrow, they're essentially monochromatic light sources. They can be manufactured to generate essentially any wavelength in the near infrared and can be tuned to correspond to a very specific vibrational or rotational mode of a target molecule. So we can select different wavelengths, interrogation wavelengths that we want to use based on the actual molecule that we want to measure, the concentration of it, how strong it absorbs, so its molar absorptivity coefficient, having an optical path length or a gas cell. But we also have to be concerned about overlapping absorbance features. So we saw in the graph that showed the absorbance profiles that there's lots of different lines for each one of those components, and some of them may or may not overlap with each other. So we have to be aware of that. So the tunable diode laser itself, this is a photograph showing a laser emitter. It's the device that's surrounded by the red box. The wavelength output of that laser can be controlled using two parameters, temperature and drive current. So typically we use temperature as sort of a coarse adjustment for the laser output, and then the drive current, that's the drive electrical current that's driven through the emitter, can be used to fine-tune that, and typically you can tune them down to around 1,000th of a nanometer. So bearing that in mind, we'll see how we can exploit those two properties of the laser in a little while. A technique that's commonly used in TD-LAS is wavelength modulation. I'm not going to go into too much detail here other than to say that it's a commonly used technique to help improve the sensitivity of laser systems, essentially by improving signal to noise ratios. So it improves sensitivity by noise rejection. So I did mention that one of the considerations when selecting wavelengths for TD-LAS is potential cross interferences. So we've got an example here on the screen of the red line is an absorbance feature of a molecule that we're interested in looking at, that's H2S. But we can also see that there are some absorbance lines of other components that might be present in the gas, such as CO2 and methane nearby. And we can see that it's possible that the absorbance of those other molecules could encroach into the area that we want to measure and possibly create a positive interference. So there's a number of ways that this can be dealt with. One way is to operate your gas cell at a reduced pressure. So in this case, we're operating the gas cell at reduced pressure of about 200 torr, and we're doing that by means of a vacuum pump. But what that reduced pressure does is it narrows the absorbance lines for each one of those components. So it makes the likelihood that they will collide with each other smaller, and thus minimizing the amount of interference between the different components. So if we put it all together, here's a typical sort of system here. We have a gas cell. Below the gas cell, we have the laser emitter. It's coupled to the cell via fiber optic cable. We have a laser launcher, a collimator that it will inject the light into the cell. It's a multi-pass cell, so inside the cell there's a set of mirrors. The laser light is allowed to bounce back and forth between them. This is also a common technique in TD-LAS. It's referred to as a Harriet cell in this case. And that's just a way of making the optical path length longer, which is another way of increasing the sensitivity of the system. So after it bounces around inside the cell, it exits out and then lands on a photosensitive detector. And in this way, using that wavelength modulation technique, we can determine how much of the laser light is absorbed and thus relate that to concentration. So those are the basics of the TD-LAS measurement. I'll now describe two techniques that we use to be able to measure 3 different gases in that one single gas cell. The first one we call line hopping. So this technique can be used if you have compounds that have absorbance features that are close to each other. So it's somewhat fortunate that the two that we want to look at, H2S and CO2, have absorbance lines which are quite close to each other. They're about 0.16 nanometers apart. So simply by changing the drive current of the laser, we can actually change the wavelength output of that laser and hop between the two lines. So in this way, you can do a sequential measurement of H2S followed by CO2 and simply hop back and forth between the two. So if you want to measure two different components that do not have absorbance features that are close to each other, obviously you may have to use two different lasers. This can also be done, we call this laser switching, and an example of this is the measurement of hydrogen sulfide and water vapor. So in this case, we have two lasers that are coupled to the same gas cell using an optical splitter. And while we want to measure H2S, we just simply turn the H2O laser off. And when we want to measure H2O, we simply turn the H2S laser off and the H2O laser on. Again, it's a sequential measurement. We can switch between the two lasers and measure the two different gases. So by combining these two techniques, laser hopping, laser switching, we can measure basically any combination of hydrogen sulfide, CO2, and H2O in that single gas cell. And we select the absorbance wavelengths that we want to use so that because of the Beer-Lambert law, one of the terms is the optical path length. It's going to be the same for all three of the components. So we have to select a wavelength that will give us an appropriate measurement signal using that fixed optical path length. So the typical switching time between the three components can vary anywhere from 10 seconds on up. Typically, we would maybe set that up for anywhere between 10 and 30 seconds to measure those three components. Here's a schematic of how the system would look if we were doing all three. So we have the two laser emitters coupled to a single gas cell through a beam splitter. We're essentially using that beam splitter in reverse in that we have the two laser sources going into the splitter and then one coming out. Again, we're coupled to the cell via fiber optic cable and injecting that laser light into the gas cell. So in terms of how this all works, we did some testing. So in our lab, we did testing with, of course, known standards. And then we put one at a site where we had access to pipeline quality natural gas to see how it would operate and compare to some existing analyzers that were also at the site. So for the measurement of H2S, we found typical ranges that we were able to measure would be a low range of 0 to 10 ppm, an upper range of 0 to 500 ppm. Typical repeatability would be plus or minus 2% of the full scale, and a lower detection limit of 0.15 ppm. So in this particular case, at this site where we were sampling the gas, the expected concentration of H2S in this gas was expected to be very close to zero. This was verified by an existing analyzer that was at the site. So the analyzer, the average reading over this is about 6 hours worth of data or so. The average reading was very close to zero. So very good correlation with the expected H2S concentration as well as in good agreement with the existing analyzer. So for CO2, typical ranges that we would measure could vary from a low range of 0 to 0.2% up to an upper range of 0 to 5%. Again, the repeatability being on the order of plus or minus 2% of the full scale and a detection limit of around 50 ppm. We had a GC at this particular site that was also measuring the CO2 concentration. GC was reporting pretty much right on 0.4% or 4,000 ppm. The results from the TDLAS system were in very good agreement with that gas chromatograph. We see a little bit of variation. This is a live gas sample, so we do see some variation in the CO2 concentration over that period of time. For the measurement of water, typical ranges would be a low range 0 to 100 ppm, an upper range of 0 to 500 ppm. Again, within those ranges, we would expect repeatability of 2% of full scale and a lower detection limit of 2 ppm. So this is kind of an interesting trend here. We see that when we put this analyzer in service, we saw initially some fairly large values for the water vapor. And as the system was allowed to purge out and dry out, this is a common thing that you see with measuring moisture. H2O molecules like to stick to surfaces and can sometimes take quite some time to get purged out of the system. But eventually, after a few hours, we saw that the H2O values were decreasing down to an expected level of, in this particular case, around 35 ppm. So I think if we would have extended our data run a little bit further, we would have seen those moisture levels drop even a little bit further. So just by way of wrapping things up, what we did find was that using line hopping and laser switching techniques combined with TD-LAS, we were successfully able to measure the concentration of 3 components: hydrogen sulfide, carbon dioxide, and water vapor in natural gas. The sensitivity, repeatability of the measurements were found to be suitable for both gas quality measurements in both the conventional natural gas value chains as well as in the renewable natural gas value chains. And the ability to do all 3 of these components in one single measurement cell obviously obviates the necessity for having 3 separate analyzers to be able to measure these impurities in natural gas. So that concludes my presentation. So at this point, I'd like to thank everyone for your attention today, and if there are any questions.
Any questions? Thank you, David. Yeah, thank you. Okay. Our next talk is measurement of natural gas contaminants using off-axis ICOS technology by Edward Orr, Alan Rilling of ABB. Dr. Edward Orr is the factory sales manager. He received a PhD in chemistry from Kansas State University and elected to pursue industrial employment. He started his career as an application scientist with NIR Systems, followed by a flow cytometry startup before joining ABB 20 years ago. For the last 25 years, Ed's focus has been process monitoring and optical spectroscopy. Ed's hobbies are hiking, swimming, and bicycling. Hey, Ed.
First of all, thank you very much for allowing me to speak here. I've never spoke here before, and I understand the ground rules are to be vendor neutral, which I will do my best. What is that? It's not on my screen. What does it say? That's not what I have here. I broke it. If you give us a minute. Pay for it. And I got $5 in my wallet. Oh. Well, so this will be another talk about measuring H2S, CO2, and moisture in natural gas. It's a hot topic in the industry. And to remain vendor neutral, I'll give a very brief overview of what we understand the needs are in the industry, and then an overview of what ICOS is. OA ICOS stands for Off-Axis Integrated Cavity Output Spectrometer, or spectrometry. That's a mouthful, and we just generally call it ICOS. So from this point forward, I'll refer to it as ICOS. Talk a little bit about the specifications you can achieve building an analyzer with this technology, how those specifications are tested, which I think is very important. We all talk about what our technologies can do, but how do we prove it? And so we'll show that data. And then a little bit of actual pipeline data to demonstrate how powerful these techniques can be. The industry, generally tariffs, custody transfer, process monitoring as they clean up natural gas. In all of these cases, obviously, safety is a big concern and asset protection. CO2 and H2O, as the bottom photograph shows, will corrode a pipe, and hydrates form from the water can plug a pipe up. So our understanding of the industry is, obviously, they want to protect their assets and run a safe pipeline. So natural gas companies or energy companies, they collect gas from various sources. They need to watch what's coming into the pipeline to ensure it's safe and to protect the assets. The profits are based on the quality of the natural gas, the reduction of repair costs, and of course the transportation of natural gas. But preserving the integrity of the infrastructure is incredibly important. We can all understand why. Worst case scenario is you have a leak in a pipeline, and that would be avoidable at all costs. So in order to do that, partnering with some industrial energy companies, speed of analysis is critical. If you're bringing something into the pipeline, you need advance warning that there could be a problem. And if you're cleaning this up, you want to know when it's really clean. So it's not just the response time, it's the recovery time of an analyzer that's very important, or a technology. Accuracy and sensitivity, there's tariff limits, so accuracy comes into play. Normally, when we talk about any optical method, we say, hey, it's a secondary method. Our accuracy is dependent on the primary method, so we don't quote it. We don't talk about it. We talk about sensitivity, meaning if you see a change, is that change real, and how soon can you see it? But here, accuracy is important. Repeatability is important. A fleet of analyzers, the industry wants to know that no matter which serial number of analyzer it is, it gives the same reading on the same sample. So the reproducibility of that hardware is very important. And the robustness. They want to put it in the field and walk away. They don't want to have to do a lot of preventative maintenance. They don't want to have to deal with, well, anything of importance on the analyzer. So, what is ICOS technology? It's an absorption technique where we bring, is there a cursor on this? Yeah, can you see the cursor on the screen? Okay, so light comes in, we bring it in off axis. That means it's not parallel with the detector necessarily. Through the back of a parabolic mirror, bounce it off another parabolic mirror that recenters the light, maintaining alignment. It makes some robustness, builds some robustness in the analyzer. And then we collect the light on a detector that bleeds through the back parabolic mirror on this side. This is continuously scanned at about 100 millihertz. So we're not tuning, we're scanning the whole time. We're collecting a spectrum, a very narrow spectrum, just a few nanometers at best, but a spectrum nonetheless. And this gives us the ability to measure two components or more potentially simultaneously with the same laser, because we're collecting a spectrum. And being off axis, it really simplifies putting two lasers in, maintaining alignment, maintaining path lengths. We also operate this at a very low pressure for the same reasons the previous speaker was talking about, that you want to minimize line broadening, which will occur as you go to higher pressures, which helps alleviate some of the error due to interfering compounds that are present. And we also, collecting the spectrum, we can pull the data into a chemometrics program with TDLS, so you can further improve the negative impact of interference by bringing it into a chemometrics type routine. So as a general example, we collect the transmitted spectrum as shown on the screen here, and we say, hey, this is our peak of interest. We're going to build a model around this, and while it's not cavity ring down, we can take advantage of the cavity ring down effect, run the laser for a bit, pulse it on and off, measure the cavity ring down at a wavelength where you're not absorbing, and you can monitor to ensure it's a diagnostics tool to ensure path length isn't changing, the analyzer's performing properly, you don't have a lot of crud on the mirrors, any number of diagnostic tools. We convert this absorbance, this transmittance to absorbance, and then we can apply chemometrics modeling. So if we look at H2S and CO2 measured simultaneously with one laser, we're looking at a red trace here, which is H2S. You can see a nice peak. We're looking at CO2, and you can see there's a lot of overlap, even with the low pressure. But there are places in here where chemometrics can easily segregate those two bands. Run the laser, pulse it. Run the other laser to measure water, pulse it. Run the other one. Remember, we're running at 100 hertz, right? So 100 scans per second. We can pulse back and forth. And you can clearly see the water band right in here. So what kind of a performance are we expecting from this analyzer? We want to measure it 0 to 100 part per million for H2S, 0 to 40% for CO2, and 0 to 500 ppm for water, with a repeatability of 0.1 ppm on H2S, 100 ppm on CO2, and 1 ppm on water. And then you can see this and read it yourself. I don't really want to read it all, but minimal detectable change at 2 part per million for H2S, 1 ppm for water. The rise and fall time. Now we're running at 100 hertz, so we can measure H2S and CO2 every 2 seconds. The T90, however, for a system, in this case, is just under 10 seconds. So you get a refresh of the real sample about every 10 seconds. Keep in mind also that we're working with a very low volume cell. We're 150 mils. So a low inlet pressure, a short T90 time, and actually a very green footprint because you don't have a high volume of gas to worry about. And the other important fact here, and this is true with almost any optical spectrometer, while you may say our performance specifications are from 0 to 100 ppm, for instance, for H2S, we can trend a couple order of magnitude larger spectral or concentrations. We will lose accuracy, but if a customer wants to clean up However they clean up their natural gas, if they choose to do that, they want to see that high level start to fall off so they know they're doing the right thing. And when they approach their limits, whether it's a tariff limit or an operational limit, they know that when they get into that range, the accuracy is there. So they can watch that the process control is actually working. This can be done in a small footprint, which is another important advantage, and I'm sorry, this is my one non-vendor specific slide, but I just wanted to show that this can be packaged in a 2-foot wide by 1.5 foot, 2 foot tall set of boxes, right? So it's small, compact, slap it on a wall, more or less. So how do we test these analyzers? How do we know if we're meeting these desired specifications? In this case, we took 2 analyzers, hooked them up to a series of mass flow controllers so we could blend gases accurately. We did 2 analyzers to show that 2 analyzers, they need to say the same thing. That's number 1. And number 2, nobody trusts just one analyzer for writing specifications. So if we look at response time, by using mass flow controllers to control, you can see that these are 2 analyzers. The tracers are overlapped. There's a red and a blue trace, and you really can't see the difference because they are in perfect agreement. The correlation, I'll get to that later, but the correlation is about 0.999 between the 2 analyzers. But you can also see the clear and distinct rise and the clear and distinct decrease. And if you blow this up and just look at this last trace that's circled, you can see here you're running just over 5 ppm, probably about 6. You can see the increase occur in about 3.7 seconds to 20 ppm. So you're getting a very quick response time. And the same thing occurs with CO2, and you would expect it to be the same type of, using the same laser, the same gas, the same cell, the same data acquisition time. So you would expect the rise and fall time to be the same for both. And if we move on to water, you see the same type of thing, where we're monitoring the water with flow controllers to control the levels. And you can see the repeatable response. It's agreeing with those mass controllers. If you look across the top and bottom, you can see the distinctive drop and the return to a high level, so the gas is turned on and off. And our response time, the response time for water is about 20 seconds. We integrate that laser a little bit longer than the other one. Sensitivity testing. 2 analyzers run again with step changes to the amount of H2S, and this is done in natural gas. Nothing here is being done in nitrogen. So we're accounting for the interference at the same time. Start at about 25 ppm and step it down to about down to 0 ppm with 2 analyzers, step it back up, the H2S concentration, and you can see the nice trending. And then just do the response time test again. You can see the exact same type of data. And there are 2 different analyzer traces here, 2 trend charts, so to speak. And you can see the good agreement. We're dropping this, at about 7 ppm per step. And if we look at the linear fit for both of those, we're at a correlation of about 0.999. So these analyzers match. They are highly sensitive. They match the flow controllers. Changes in the analyzer should, let me reword that. It doesn't force you to question a change in a trend chart. Is that my analyzer or is that my process, right? The demonstration that this analyzer trends very nicely and is very responsive. The other thing that's very important, TDLs, they're all tunable diode lasers, right? They're all tunable diode lasers, and there's temperature sensitivity with those. So how well can you protect a technology from outside temperature changes? We dropped 2 of these analyzers into an environmental changer increase the temperature by 15 degrees per hour over the course of, so 3 step changes in the temperature, 15 degrees each step. And we're looking at plus or minus 2% on the H2S, and you can see as the temperature changes, the dotted lines are the performance specification requirements, upper and lower. And you can see that trend through this 45-degree temperature change stays within specifications for the analyzer. There's some touch sensitivity here. I'm actually nervous and my hand's shaking when I'm doing this. CO2, the same thing, although you can see the effective temperature. You can see how it changes the result, but it's changing it within the specifications. And the same thing for water. You can see the noise it creates. You can see that it does change the performance of the analyzer to a degree, but it's within that plus or minus 2%, straight across the board. And you put an analyzer in a shelter, you're not going to see a 45-degree temperature change, right? So this is a very extreme case. Cross interference. This gets a little bit confusing, but if you look at H2S at 0, 10, and 20 parts per million, and vary the ratio of CO2 to CH4, CH4 methane, natural gas, CO2 another contaminant, and step change that, you can monitor the CO2 and you can see how it's changing as the ratio is altered. But you can see the H2S is staying very flat, so there's no cross interference. Conclusion of that. Increase the amount of H2S. Repeat, changing the ratio of CO2 to CH4, bringing it back up. That's board flat, right? You're not seeing any impact on the results. And same thing when you take it up to 20, when you take the H2S up to 20 ppm, the same type of result. You're changing that CO2, and it really has no impact on the H2S measurement. And remember, once again, this is 2 analyzers, and the traces are overlaid, so they're still matching quite nicely. Hit the right button that time. Testing the background interference to take that another level, and this one gets hard to explain, but if you take C2, C3, CO2, and methane and vary the ratio of those components at 20 ppm H2S on 2 different analyzers, without going into what all the squares and diamonds are, but you have 2 analyzer results here, and you're changing the amount of, oh, doggone it, did that again. You're changing the amount of C2, C3, CO2. The dotted lines up high and down low are representing the desired specifications, and you can see by altering those concentration ratios that we're not really having an impact on the specification of the analyzers. And that repeats for CO2, running that at 5%, and about 240 ppm water, the same type of things. You can see water has a lot more sensitivity there to background, but it's still within the specifications of what's desired from the analyzer. So we pick ICOS technology because it's very robust. We can measure more than one component. We can create a spectrum, dump it into PLS. We can operate at very low volume, very low pressure. We can generate path lengths in the kilometer regions to get low levels. And we can also account for interference not only with reduced pressure, but by taking that spectrum that we collect and using the chemometrics technique, factorial analysis, to help compensate for some of the error induced by interference. And we tested that versus varying the backgrounds. We tested 2 analyzers performing exact same way. We tested the specifications in an ambient chamber to alter the temperature that the analyzer is running or exposed to ensure that the analyzer itself is temperature stable. So using this technology in an analyzer, it hits all the key points that people are looking for with a fast response time, both increase and decrease. So if we look at two upsets that occurred at a custody transfer station, the one on the left, you can see the H2S was way over limits. It's 15 or 10 or 15 ppm tariff limits on H2S. And this was up almost to 40 ppm. So this natural gas was not put into the pipeline. It was allowed to, it was taken out and treated, so to speak. It was diverted, I guess the term would be, and scrubbed clean. And you can see the cleaning process is going along, and in about 5 hours, well, actually in about 4 hours, it was below the tariff limits, and they could then put that in the pipeline. The same thing happened with H2O with an upset of water, and the upset was caught, the gas was diverted, dried, and then it was allowed to be pumped back into the pipeline because it was well within the tariff limits, and I'm way ahead of time. This is some real pipeline data. Probably missed a few slides doing this. Every time I touch this keyboard, I advance it. This is also H2S before it goes into a pipeline for transport. And you can see that there was a huge amount of H2S in this gas. So it was diverted. H2S came down, caught another upset from the gas supplier. It was brought down, and then it ran smoothly after they cleaned it all up and fixed the problem so that it could go into the pipeline. The H2S was low enough. Same thing with CO2. It trended like the H2S. This is not cross interference. We've demonstrated that we don't have that. There were also alternative analyzers in use to show that. And you can see the same type of problem, a general upset from the supplier of the natural gas, and it was diverted until the supplier could clean it up. If you blow up those regions, you can see it quite clearly, the regions that were circled. Here's the H2S upset starting, then it took off, kind of mellowed out when they diverted the gas. Same thing with the CO2. See a little bit of something here. You kind of see it down here. The timescales are a little bit shifted here, but whatever was upsetting the H2S was also upsetting the CO2. So, off-axis ICOS technology. We explored this technology in conjunction with some industrial partners. Industrial partners wanted green, low volume analyzer, low volume technology, allows for a greener footprint, speed, not only for rise time, but decay time. So you watch concentration go up, you want to see that quickly. Goes down, you want to see that quickly as well because you know the problem's solved. Sensitivity, when you see that change, you want to make sure the change is real. We proved that with the mass controllers, that we can ramp up, ramp down, extreme levels, stepwise, track that perfectly. 2 analyzers measuring the exact same result every time, side by side on the same sample. We can, an incredibly wide dynamic range. Once again, once you go outside of the desired specifications, the accuracy tails off, that's expected. But the ability to trend is still there, so that if a sample is increasing and it's well above the range of the analyzer, you know it's still going up. It won't start to drop because of being out of the specification. You just won't know how high it is. You have a good idea, but you won't know for sure. And when it starts to come back down, for instance, H2S, you know that it's decreasing. Whatever you're doing is working. Now, you may not know how good, you know. You can't say it's good to plus or minus 0.1 ppm, but you know it's falling, and that's the goal. And when you approach the limit, then you need the accuracy. And that's what ICOS can bring you, that wide dynamic range, very sensitive, very accurate, trending well beyond its desired range, and good analyzer-to-analyzer reproducibility. And of course, it's very robust. That's been proven in other applications in the field, but once again, we don't worry that much about alignment. The way our optics are designed, we can monitor the effective path length. If there's a problem, we'll alarm it. With that type of technology, you could conceivably do real-time path length corrections. I know we've experimented with that. So there's a lot of things that make this technology very ruggedized for field applications. On that note, I'm sorry I spoke way too fast, 20 minutes versus 30. I will say, like I said, this is vendor neutral, I hope. That's the goal here. If you want to know about this product, just come to the booth. There's people a lot smarter than me down there that can answer questions. I'm a chemist. I'm not an engineer. I can't talk about details of the design. I don't know anything about natural gas other than what a spectra looks like. But from a spectroscopist's point of view, very happy with this technology. Is that it? Thank you.
Any questions for Dr. O?
Right? If that answers. I'm trying not to promote a product here. Well, I am, but I'm not. So.
Thank you very much. Thank you. That's some gift from the conference.
Oh, thank you very much.
Thank you.
Okay, so that's it for today. The exhibit hall is still open, and I think the bar will be open at 5 o'clock. If you've got score sheets, if you can get them to me, either bring them to the front or just put them on the table by the door, I'd appreciate it. Hope you all had a good day and have a good evening. We'll see you back tomorrow, 8:30 start. Thanks.